is everywhere, but the real power comes from turning that data into intelligent decision. From recommendation systems to fraud detection and self-driving systems, machine learning is already shaping the future of every industry. With that being said, I welcome you all to this session on machine learning with Python full course. Before we begin our session, just a quick info guys. If you want to build a strong career in AI and machine learning, then Simplilearn offers an advanced professional certificate course in generative AI and machine learning, designed in collaboration with AICTE Consortium of IIT Kanpur and powered by industry partners like Microsoft Azure. This program includes live online classes, hands-on projects, expert mentorship, and career support, helping you move from fundamentals to real-world AI applications. Now, coming back to the course. In this course, we will learn how to use Python for machine learning from scratch to advanced levels. We are going to start with Python refresher and maths and statistics. Then we are going to move into data processing and exploratory data analysis. After that, we are going to explore core machine learning concepts like supervised, unsupervised, regression, classification, clustering, model evaluation techniques. We will also understand advanced areas like deep learning with TensorFlow and Keras, NLP, reinforcement learning, and real-world ML project building. And finally, we are going to apply everything through hands-on industry projects like sales prediction, customer analysis, recommendation systems, and predictive modeling. By the end of this course, you will not just understand machine learning, but you'll also be able to build real intelligent systems using Python.
So let's begin with this journey and try to understand what is machine learning and why is there so much buzz around it. Let me go through what all we would be covering in this particular course, and then we begin the discussion. So if we talk about a learning path, the first, topic that we will be covering today is Introduction to Machine Learning, which focuses on the basics of machine learning. Second is Supervised Learning, Regression and Application, which focuses on supervised learning with an emphasis on understanding and implementing different types of regression models. Third is Supervised Learning, Classification, Applications, like basically we're trying to cover that what are the different learning techniques available in the machine learning. So first technique that we would be covering up is supervised learning. Under supervised learning, we would be covering up regression as well as classification. Then we would be moving on to the ensemble learning method, which focuses on advanced ensemble methods to enhance the performance and robustness of the models. Then we would be moving on to unsupervised learning and finally recommender system along with the application. What is machine learning and why is there so much of buzz? Why are you here to learn machine learning? Let me put this in another way. So basically, we want the machine to get trained with our data. We want the machine to learn from the data so that it can predict data. What kind of data that we want to predict? Why do we want to want these predictions? Right? Because now are we living in the digital technology where data is all around us? Even this, session is data, right? When all the material that has been sent to you is data, anything on the news which is coming is data, anything doing for entertainment is data, e-commerce is data, your work profile is data, because we are living in huge amount of data. Data is all around us. Do you think, is there any escape from data now? No, not now. When I used to take sessions 5 years now, and 7 years before, the scenario was a little different, trying to adapt. But I don't think so. There is now any survival without data. Can you survive without this data? Not moving on social media. And, one day, as it says, if the internet stops, do you think your life also stops? Your mobile phone is lost. Everything is lost. Isn't it? The data has become a lifeline, and now we see several applications which are working or the concepts that are being based on data. Now it automatic translation. Translation has not become difficult if you want to convert something from English to German, German to Spanish, any language translation is right there. We speak to the machine and we get the translation. Virtual personal assistants are there. image recognition, email spam filtering. That's actually comes under the domain of machine learning. That it, based on the algorithm or the pattern or the text or the words which are there, it is able to filter out whether the mail is a spam or not. So, what do you think would be the criteria? Generally, the mails with spam are saying that you have a lottery system, other system, or there is a bonus, so that becomes your email spam filtering. Then we have the text and the speech recognition, medical diagnosis, online fraud detection, is there, where we want to detect how is the online fraud happening, web search and recommendation engines, and of course what is going to be the traffic prediction. Not only the traffic prediction on the roads, but it also related to the traffic going on to a particular website, whether that website is going to get crashed or not. Data becoming now difficult to handle because it's digital data. Understanding data, everything numerically is difficult. Earlier the data was this much, it could be handled. Now it's becomes like this much and this much and this much, and it's increasing. So we need certain algorithm, we need technologies which can help to analyze so that we can improve our performance. But if we look at on the overall scenario, still there is a lot of confusion about the AI, the machine learning, and the deep learning. Yeah, what is the subset or the issues, like what is artificial intelligence, machine learning, and deep learning? Are you able to distinguish between the three? So this is one of the initial chess, developed by the computers. IBM Deep Blue chess program developed in 1997. When was it developed? It was developed in 1997 by IBM. And this particular program was strong enough to defeat the world chess champion at that particular point. His name is Gary Kasparov. Okay, he was capable of defeating the world chess champion. Getting my point? Right? And then we have this IBM Watson under machine learning. So AI is the bigger branch. All right. Artificial intelligence is the bigger branch, right? Under which we have the machine learning subset, right? Which we are going to study. In machine learning, basically, it works on statistical algorithm. That is why we say that before learning machine learning, it is important to have a good concepts and knowledge of statistics that helps to understand. So based on statistical foundation, statistical algorithm, the machine is capable of doing Google search algorithm, Amazon recommendation, and email spam filtering. How, like we just saw, that it is capable of filtering the email. And then finally, we have the deep learning, which is also under machine learning, in which we have the AlphaGo, the natural speech recognition, and the level 4 automated driving system. The scenario has changed and we are into the AI revolution. So the bigger branch is still AI. We are seeing, we are the, witnessing this revolution in front of us. Under AI, we have the machine learning. Under machine learning, we have the deep learning. And under deep Gen AI task, right? So when we talk about the Gen AI task generation fine tuning, we have the agents, automation, and the virtual assistants. And this Gen AI is now capable of even doing a lot of text generation that we see. We ask a lot of things to the Chat GPT, other models like Gemini, Copilot also. We want to generate images, video generation. All these things are being possible. AI that we are talking at the moment is only and only related to the software. Through software, we are able to provide or give intelligent answers. But what is basically the difference between a traditional programming and a machine learning programming? So let me explain you with this particular example. So in traditional programming, again, we have this data, right? that this is my data, which is 1, 2, 3, and 4, right? And over here, we have machine learning algorithm where we have 1, 2, 3, and 4. Okay, the data has not changed. I'm giving you a very simple, example. Now, if we talk about the program, initially the program, and we talk about C, Pascal, Fortran, even C++ and Java, and even Python, they are capable of giving logic. Now, if I want to distinguish that, what are the numbers? What is the logic behind that these numbers are even or odd? So simply we understand the logic that if I talk about Python, I percentage 2 is equal to 0. That means if the remainder divided by 2 is 0, then the number is, it is odd, right? Else it is odd. Getting my point? Yes or no? This point is getting clear. So now, even if a number 10, it would automatically give me that this is going to be an even number. And if I give the number 57, it is going to be odd. But now, machine learning, how things happen, I give the output along with it. I say that 1 is odd, 2 is even, 3 is odd, and 4 is even. Got it? Now the computer, based on certain statistical concepts, algorithm will try to detect that when I feed the number 10 over here, that it is going to be even. Can it predict me as odd also? Yes, the prediction can be wrong also. Clear? But if the algorithm has to be good enough that it is predicting that 10 is even and 57 is odd. So, coming on to the concept, the first kind of learning is known as supervised learning. What is it known as? Supervised learning. That if this is my known data, this is already now images, that this is my input, and I also feed the output. When I feed the input as well as output to the machine, it becomes my labeled data, right? That means this is an image of an apple. I feed it into the machine, and when I feed this apple, it says, predicts that is this apple or not, and it predicts it's an apple. But it can predict wrong also. So might have seen sometimes the chat GPT also predicts, gives wrong answer. The image development, Ghibli and all give wrong answers. It's the biggest fear, that these, if a wrong or a incapable data is set to them, then it can give false and nonsensical and fabricated information also. So this is the fear that we are now moving ahead. Right, Ajay? Charan? Hardik? But if we talk about clear system, if we talk about the traditional systems, expert systems were working that we have a user, we are trying to give the query and then try to get the output out of it, right? If this is my query and this is how I get the output out of it, and then I try to infer what is it. But inference is not coming from the data, but this data, it's coming from data, but this data is created from an expert. Now, what do I mean by that? Let me explain this to you. Expert can be a cardiologist, a lawyer in different domains, right? A cardiologist, a lawyer, somebody from in the finance domain, maybe for 30 years, 30 plus years of experience. And we created if else knowledge, inference knowledge, that whether you are capable of getting a loan or not. And if I have a cardiologist, some information has been fed that maybe your BP rating is this much, or your terms. If that is matching to the inference engine, that's how it will give the output. So what happens? For example, if you are a user and you enter to the user interface, maybe all your blood reports, your BPs, and your test reports, all things are given as the user interface, right? And then we do the inference engine, and based on this knowledge base, we get the output, right? So what has been replaced now? Rather than knowledge base, it is completely based on the original data, and things have become complicated on images, on non-structured data. So do we understand supervised learning now? Can I say more the data, more my system becomes intelligent? It is only capable of recognizing hexagon, triangle, and square. And if I add a shape of a circle, maybe a parallelogram, maybe a rectangle, it's capable of analyzing that. So that is where, the systems are getting modeled, because the data is becoming huge day by day, right? So this is supervised learning. So under supervised learning, we have the label data. What is label data? We have the input as well as the output, where we try to train the model. After the model has been trained, based on the test data, we try to do the prediction, whether it is a square or a triangle. Clear? We will initially start with supervised learning, that we have the input, the output. We will try a model. So where will we do the model? That means now the data, the 70% of the data will be used for training, and 20 to 30 percent will be used for testing. Then it will predict the output. Okay. And as I've been telling you, there is a very strong relationship between machine learning as well as statistics part of it, right? So statistics is a field of mathematics, but when it is combined with computer science, the machine learning, it becomes statistics and machine learning. The idea of statistics is that it helps us to draw inferences, relationship between variables, whereas machine learning gives optimization, prediction, accuracy, etc. Right? And then we have prior assumptions about the data, some knowledge about the population usually required. This is none. Dimensionality of the data usually applied to the low dimensional data. And knowledge overlap, there's no ML knowledge required when we study statistics. But in machine learning, some statistics knowledge is usually needed, as it is becomes the foundation for few algorithms. So if you do not know much about statistics, there is nothing to worry. It's not very difficult. Definitely concepts of probability would be required. So I would just request you, the learners, to get familiar with the concepts of probability, conditional probability, Bayesian theorem, and probability distribution. So this is what I expect from you all. Got it? Right? And to make the picture a little more clear, the boundaries are not very crisp now because there is data everywhere. But to make the picture a little more clear, that, when we start with initially Python course, we are doing visualization, exploratory data analysis, maths, and statistics. And when we try to do overlap between AI, machine learning, deep learning, we get this data science. So data science becomes the foundation for AI, ML, and deep learning. If I technically ask you what is learning, and now you might have been hearing this word agent, it could be a human agent, it could be a robotic agent, it could be an AI agent. So if we talk about a little more technical definition of learning, basically we are trying to improve the behavior based on the experience. When we say you are a very learned thing, you experience, that means different types years of knowledge. The range of behaviors is expanded. The agent can do more, right? The range of behavior is expanded and agent can do more. The accuracy on the task is improved. The agent can do things better. and the speed is improved, the agent can do things faster. So what is the idea of learning? If you see this, means that DS, okay. So if we talk about learning from the machine as well as from the human point of view, this definition is valid. That it is the ability to improve our behavior based on our experience, right? It's not always about acquiring new skills. That's one of the things, that range of behavior that you are, driving, swimming, stitching, cooking. Of course, the range is increased, but also accuracy. By doing the thing again and again, doing learning increases my accuracy as well as speed. And if we now see technically in machine learning, the different types of learning techniques are supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. So all these kinds of actually learning come from the fact that how we as humans also learn. So do you also agree? Only agree through training and testing? Training and testing happens when we are going to school, we are trained and then we are tested in universities, colleges, or even this session. Is there any other way we learn also? Do we learn through observations? Do we learn through our mistakes? Do we learn? There are different kinds of learning also possible. And exactly the same thing we also try to replicate in our machines also. So one of the learning method is observation. So one basic difference between supervised learning and unsupervised learning. What do we mean by supervised and unsupervised learning? Supervised learning says that this is my data, right? Are my apples, right? And I tell them that this is my image, these are apples. I data 70% of my data is used for training and 30% of the data is used for testing. Label data is given in, so absolutely correct, Mega. Label data means supervised learning. And then the model predicts me that it is an apple. And what is unsupervised learning? Do I have a label data? No. I have not told that this is an apple or this is a banana or this is a peach. But the model or the algorithm, sorry guys, is capable enough to distinguish between the three of them, that this is my apple, this is my peach, and this is my banana, right? So initially we will, build concepts on this supervised as well as unsupervised learning. The machine is given huge sets of data that are not labeled as inputs to analyze. The machine needs to figure out the output on its own, where it identifies the patterns. And the two types of algorithm which come under unsupervised learning are association and clustering. And K means for clustering problems and a priori algorithm for association rule learning problems, right? And then we have supervised learning. The input is in the form of raw data that is labeled. The machine is already fed with the required feature set to classify inputs, divided into two types of problems, regression and classification. And then we will try to understand different regression algorithms. This is the first stage that we are going to work on. Clear? So now let's understand what is self-supervised learning, Here we have the input data. Is it labeled? No, this is not labeled data, but we have partial labeled data, that this is an orange and this is a banana and its quantity is less. And here both the types of data are mixed machine learning model, and this is my unlabeled data to predict the output. So it's an apple. So this is my input data, right? This is my partial data. And when I combine them together, prepare the model, I get the output. Clear? And reinforcement learning, the most effective way of learning from which we as humans learn a lot. That means from our mistakes, from our feedbacks, from our punishments, from our rewards, right? So if this is the input given to the machine and the machine predicts that it is a mango and I give a feedback, wrong, it's an apple, it notes it down, and now when I feed the apple again to the machine, it says that it is an apple. So making the overall picture a quick recap that basically, if we talk about machines, there are three types of learnings. We have the supervised learning where we have the input and output. And this supervised learning is capable of calculating error. That is output minus the input. And what is because why are we capable of calculating error in supervised learning? Because we have the actual output over here, right? And based on the actual output, is my machine predicting the correct result? That if it is an apple, is it actually telling me an apple or not? Or is it telling me this is a cherry? So I can calculate my error. So the biggest advantage or the simplest way to learn is supervised learning, where we are capable of calculating the errors, right? Here we have unsupervised learning where we do not know the output. It's just trying to do the clustering and association between the objects. And the other type is reinforcement learning that is not going to be part of this journey. That's generally taken into deep learning concepts that where the machine learns from its, punishments and rewards, right? And of course that we are capable of calculating error. Again, I'm telling you, in this particular course, we are going to try to cover supervised and unsupervised learning, concepts, algorithms in detail. Now, moving ahead to supervised learning. There are two types of supervised learning. We have regression and then we have classification. We have regression as well as classification. Now, what is the difference between the two? Please try to understand. Under supervised learning, if the output, it's all about output. If the output is numerical, then this is known as regression. And if the output is categorical, then it is known as classification. Getting my point, learners? What we are trying to achieve that what is going to be the temperature tomorrow. So if it gives me that tomorrow it is going to be 84 degrees Fahrenheit or any other value, then this kind of algorithm is regression. But if I want to predict whether the temperature is going to be cold or hot, this is known as categorical data. Clear? So the regression works on numeric and classification works on variable and categorical. Two types of numerical data. One is discrete, another one is continuous. Do we understand that? And if we talk about categorical data, do we understand nominal and ordinal data? This is what is covered in data science class. So basically, data types are divided as qualitative and quantitative. Very, very important when you divide the data as qualitative, it's categorical. Ordered data is something, like rating, ranking, they come under order. Feedbacks of movies. Nominal is that there is no order as such, the color of the eyes or nationality. And quantitative is numerical values. Continuous, which can be divided, such as distance, salary, price. And something which cannot be divided is example, cats, etc. So now I hope the concept of regression and classification is clear to everybody, right? So making your concept more clear. that regression is something when the task of predicting a continuous quantity, that I want to predict the price of the house. That price of the house in 2014 was this much. Then in 2024, it is this much, right? And then what will happen? What will be the price in 2034? Clear? So since price is a numerical quantity, it comes under regression. And classification, as I told you, that if I want to separate whether the mail is a spam or not, that comes under a classification problem. Clear? So now we will begin our journey in this machine learning through supervised learning. First, we will try to complete algorithms which are like simple linear regression, multiple linear regression, polynomial, support vector, decision tree, random forest. We are not covering neural network. All the others will be covered. Similarly, in classification, we will cover logistic, k nearest neighbor, support vector machine, naive Bayes, decision tree, random forest. Again, neural networks are not covered. Yeah, so with this, we come to the end of the introduction. And if you will now look at your slide, the ebooks, that is lesson number 2. Now we can begin with lesson number 2. So just have prepared the foundation for that. So let me show you the lesson number 2. All right, so we are now starting with this. I hope now you would be able to locate this particular file in your LMS, in your material. Please look at that. So analyze the distinctions and applications of machine learning, deep learning, artificial intelligence through the real world examples of various technical applications. Differentiate among various machine learning models and explore each model learns from data to predict outcomes. Explore Python libraries for effective data manipulation, visualization, implementation, and machine learning algorithm. So the business scenario says that ABC is an e-commerce company which is struggling with a surge in fraudulent transactions on its website. The manual review process for transaction has caused delays in order processing and led to negative customer experience. To address this, ABC will use machine learning algorithms to detect real-time fraudulent transactions. So machine learning algorithms are capable for detecting the fraud transaction. And these algorithms will be integrated into the company's transaction processing systems to flag suspicious transactions and prevent fraud. Additionally, the company will use these algorithms to predict the customer behavior on the past purchase history, thereby improving the recommendation engine's performance. Now everybody is using mixture. Everybody wants the best. The more you learn, the best output you get. And when I say best output, you want the prediction to be highly accurate. So when your report goes to a machine learning or an AI machine, it has to give accurate result that whether you are, that predicting that, it should be accurate enough to predict that, yes, you are, you know, uh, you have a tendency to have cancer or not, So not only one technique will be used, it will try to use mixture of techniques to get the best results. Got it now? So now are we clear what is machine learning? So machine learning is a subset of AI that assists systems to learn and improve automatically from the experience without being explicitly programmed. Arthur Samuel coined the term machine learning in 1959. It enables programs to learn automatically, making computers more intelligent without human intervention. But human feedback is extremely, extremely important because, see, ultimately, machines are not genius. We have to tell them that this is, an acceptable result or not. So who is known as the father of machine learning? It's Arthur Samuel, and he coined the term machine learning in 1959. Father of AI, that's John McCarthy in 1956. Yes, John McCarthy in 1956. Are we now more clear what is the difference between the traditional approach where we had the data and where we were programming explicitly the output, right? And the machine learning approach, based on the algorithm, based on the data, the patterns it understands, it predicts the output. That is why statistical techniques, algorithms are the foundation for machine learning. It automatically learns the features and reduces the need of manual featuring. Clear? It handles complex and unstructured data such as images, text, audio without requiring extensive pre-processing. Performance improves with more data and learning iterations, enhancing accuracy and generalization, right? And now do we understand this Venn diagram also, that machine learning, deep learning, AI are often used interchangeably? So AI encompasses simulation of human intelligence in machines. So self-driving cars are, AI. All the robotics come under the category of AI. But machine learning, Amazon Alexa, where we are giving it specific instructions and it gives us output. And when I talk about deep learning involves neural network, which is going to be your next stage after machine learning, to understand how neural network work, how are they capable of understanding complex pattern recognition, such as recognizing patterns in images, speech, text, etc. So, what are the examples of machine learning? In a chess game between a computer and a person. So why do you think that, why is this chess game always coming into the picture? Why do you think is the chess game always coming into the picture? Well, when we talk about human beings, a person who plays chess well is said to be intelligent. It's an intelligent game. Agreed? Is said to be intelligent, and even if the results go wrong, there's no harm. There are no catastrophic results, Even if the person is winning and says the machine is winning, it is not that harmful. Yeah. So that is why, was one of the way where AI exploded in, intelligent gaming systems, theorem solving. That is why chess, AlphaGo, these are the games which you will, read or see when we talk about a little history of AI. So in a chess game, between a computer and a person, the computer uses AI to analyze the game, predict moves, decide its decision. AI uses machine learning to figure out the opponent is a beginner, intermediate, and an advanced level. How the AI uses machine learning to identify whether you are a beginner, intermediate, or an advanced player? By predicting our moves, based on our moves, it will immediately judge, that you are a beginner or intermediate or an advanced level, right? And you might be playing a lot of games where there is AI and other, graphics games over there, especially the young generation, right? Well, I don't, but you can, how smartly, they are capable of hiding things and they become smarter. The level changes, as you are also becoming smart, the level of the game becomes smarter, right? We all observe that. So AI decides its next move against the opponent using a complex neural network that learns various features, patterns from the data, right? Then, of course, many applications are there. We see machine learning all around us in spam filtering. Spam filtering actually use knife-based classifier, social media analysis, customer service chatbots, now a lot of available online recommendation. We all see that. Sentiment analysis. How does the sentiment analysis happen? Anybody who has an idea? Based on the words and especially the emojis. Is it a smiley? Is it a angry face? Is it a sad face, crying face? All these things are taken into account. So these processes allow computers to learn patterns from the data, make predictions, predict outcomes, classify target, feature, and improve performance. So that's what we want. Machine learning, that they help to predict the outcome, what is going to be the price of the house or any other thing after 10 years down the line, classify target features based on the similarities, and improve the overall performance of the system. And we have seen, is there a very, very strong relationship between the data and the output? Yes. The amount of data, if it is more, of course, the output or the quality or the prediction also increases. Where the red line is the quantity, and if it is high quality data, we get better results, better insights, and better predictions of the output. So, of course, maintaining the quality, authenticity, and removing the errors, all these points have to be taken into account when we are talking about the data and the machine learning algorithms. Clear? Right? So when we talk about types of machine learning, ML can be divided into 4 main categories, each characterized by its capacity to predict the conditions or identify the patterns to produce outcomes, such as what is supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. Now, I think the distinction is clear. Supervised learning, we've done this. What are the 3 main points under supervised learning? First is the label data. What do we mean by label data? It will have the input as well as the output. Second point is splitting of the data into training and testing, right? Generally, training happens on most of the data and testing on the rest of the data. And third is calculation of the error. Because in supervised learning, we know the actual output also and whether it is predicting it right or wrong. Clear? And some commonly known, supervised learning algorithms are linear regression, decision trees, logistic regression, support vector machines, etc. So some examples of supervised learning are predicting temperature rise based on the yearly temperature trends. Predicting, why supervised learning? Again, predicting temperature rise. It comes under regression because it's a numerical problem, right? Numerical output. Predicting crop yield based on the seasonal crop quality changes, again regression. Sorting waste based on the known waste items corresponding to the waste type. This types comes under classification or filtering. So under supervised learning, calculation of error is also going to be an important aspect of machine learning, because we have to be very clear that the output of machine learning will always not be 100% correct. Clear? Now these examples making the picture more clear? And if we talk about unsupervised learning, very much used to, identify different parts of the object, image segmentation for object detection, identification of user groups based on commonalities, identification of anomalies over geographical landscapes based on the data patterns. The unlabeled data set is provided to an unsupervised learning algorithm to discover hidden patterns and to recognize their relationship. So it's not that unsupervised learning is not important. It is equally important to analyze different features, different relationships in the data, right? Rather, this is the algorithm which helps us to discover the hidden patterns and discover the relationships. Clear? And now coming on to the unsupervised learning example, it automatically groups the images based on the similarity that this is unlabeled data. Based on that, it is capable of distinguishing the middle-aged people, old-age people, the young, the infants, the teenage, etc. Got it? And what is semi-supervised learning? As I've already told you, it uses a combination of small amount of labeled data. Sometimes, the data is, that's one of the constraints that we see in data is not completely labeled. A large amount of unlabeled data is used for training. Like supervised learning, it aims to learn from a function that can accurately predict the output variable from the input variable. It uses the unlabeled input to assist the learning process by collecting more information, improving model generalization. So it falls between supervised and unsupervised learning. So suppose this is my raw data and I have partial that this is adults and these are kids. Then the machine automatically distinguishes between babies, teens, and tweens, and also distinguishes between the senior citizens, youth, and adults. Got it? So it automatically learns the correct, groupings of the kids or the different people into teens, tweens, and babies, and the adult ones into these category. Clear? And another example of semi-supervised learning, which we see it practically, that was your question, Megha, that Google Photos is popular example of semi-supervised learning, that when a picture is taken, it gets stored in the Google Cloud platform. And from slowly, the Google tracks, whose picture it is, at what place it was taken. So in various instances, uploaders label images. Despite Google's lack of knowledge regarding image names, its algorithm can identifying by analyzing visual features and shapes and colors, and it does that. It does a lot for me. It's able to identify my friends, my family, in which location I was and where. And reinforcement learning is a type of machine learning where algorithms learn from the environment by performing actions and receiving either rewards or penalties as feedback. If the program finds correct solution, the interpreter rewards the algorithm. If the outcome is incorrect, the algorithm is penalized for incorrect predictions. It must reiterate until it finds a better result, right? So ultimately, reinforcement learning involves an agent. It interacts with an environment, learning from the rewards and states to choose from, and then based on the output, it gives the best action. And if it is an error, it learns it again. All right. So this is my input raw data based on the environment, reward, state, and action. It's capable of detecting them separately. Okay. So the example is this type of learning is seen in YouTube recommendation where the user searches for a particular song. The program shows the list of available songs. So when a user selects a specific song, the system trains itself to remember and deliver similar results for future searches based on the user's interaction, like views, shares, etc. So this is the concept on which recommendation systems work. So other examples of reinforcement learning are game where players can play with bots, autocorrect tools, search recommendation engines, self-driving cars, and then the Python packages that we would be doing in for machine learning. We are aware about NumPy. It's a very powerful tool for numerical Python computing. Matplotlib for drawing data visualization. Pandas. So I hope you all are aware about NumPy, Matplotlib, Pandas. But we will be working more on the Scikit-learn, file, which consists of different algorithms. But the pre-processing, the other part is also being taken care before we feed into the algorithm. So a quick recap. So machine learning refers to the machine's ability to learn from the data and replicate human behavior. AI includes machine learning, deep learning, each with unique capabilities for simulating intelligence. There are four main types of machine learning: supervised, unsupervised, semi-supervised, and reinforcement learning. Python packages are folders with modules that organize code for easy reuse and maintenance, improving the development efficiency. Now, clear? So now let's go in for a knowledge check. Question number 1. Yes, learners, are you there? Which of the following best describes the machine learning? A, B, C, and D. Question number 2. Which example illustrates the use of machine learning to enhance customer experience in an e-commerce company? What distinguishes between deep learning, machine learning, and AI? Yes, it is a subset of ML that uses multiple layers for complex pattern recognition, such as recognizing patterns in images, speech, and text. Right. So with this, we come to the end of the very introduction and basics of machine learning. Yeah. So what I'm looking forward is, this is the overall picture of statistics that we have. The learners who have already done data science are aware about it. The ones who are not aware about it, the different types of statistics that we have is descriptive. Under descriptive, we have measures of central tendency and measures of variability. Under measures of central tendency, we have the mean, mode, and median. Under measure of variability, we have the range, variance, and dispersion. And here we have the inferential statistics, how we infer the results. So this is the important part that we are looking at, that includes confidence interval, hypothesis testing. So you can do a lot of search on inferential statistics. And this is what I am saying, that statistical inference, constructing confidence and intervals on population, hypothesis testing, that is what I'm looking. And what is the advantages of these particular program? Because ultimately, probability in data science and AI play a very, very major role in understanding uncertainty, predicting outcomes, how probable the correct the output is. Even the LLM models, the chat GPT is predicting on the probability. Okay, this is the next word. So if it is 70% above, then let's predict the output. How do we model complex system? Enhancing AI. And it is the statistics and the probability together which help in exploratory data analysis and give meaningful insights and features. So as we are going through this flow, we understand we are going to start with supervised learning. What is supervised learning? Before supervised learning, I would like you to cover, cover the basic concepts of machine learning, which I've prepared through my PPT, and then we will move on to what they have shared. Okay. So the first thing is regression. What are the two main algorithms which come under supervised learning? Yeah, regression and classification. What is the difference between regression and classification? Basically, regression happens when the output is numerical, and classification happens when the output is categorical. All right, so I start with my PPT again so that it helps and it gives you strong foundation, clear concepts so that we can move along with that. So if we talk about the first knowledge check, what is machine learning? Correct answer, it is C, that it is an autonomous acquisition of knowledge through the use of computer programs. Second question, what is the key difference between supervised and unsupervised learning? A and B are both correct. What's the key benefit of using deep learning for tasks like regression? How do I, okay, you've written yes, okay. What's the key benefit of using deep learning for tasks like recognizing images? Yeah, they can learn from complex details from data on their own. That's the idea of deep learning. That's the use of neural network. Absolutely correct. All right. So now we start with the concepts of machine learning under supervised learning, which are valid for regression and classification algorithms. Whenever you will say, machine learning, these are the basic questions that will be asked, right? So if I talk about machine learning or supervised learning, what are we trying to, do in supervised learning? What is the main aim? What is our main objective of supervised learning? But prediction of the data. Okay. We would call it prediction of the data, future based on given data, right? We want to predict. And is this prediction always correct or it can be wrong? Can be wrong. They can be errors, right? Right. And so they should be a limit of accepting the errors or rejecting the result, right? There should be some way of accepting and rejecting the results. We all understand this very in a conceptual, subjective matter. Now let's try to understand it on the basis of mathematical functions, right? So here we have the plus over here and here we have the minus over here, right? This is my data set. This is my x-axis and this is my y-axis. These are given as my data, right? And what are we trying to do over here? We are trying to predict the output. So what are we trying to predict? The data, that what is the value of this question mark? What is the value of this question mark? All right. And what is the value of this question mark? Right? Is this question mark a plus sign or a minus sign? Can you tell me? What is this question mark, a plus or a minus sign? What about this? What about this? So this is my first question mark, second question mark, third question mark, and fourth. So based on your observation, can you tell me what is this first? Do you think it is a plus or a minus sign? What does this particular data point represent? Is it a plus or a minus? Because this particular data point is more close to the plus. So if there are chances that this is going to be plus sign, more chances. Yes, it can be negative also, but we can say 70 to 75% or 90 to 95% chances are that this is going to be plus. What about the fourth one? This is negative. Now, what about the second and the third one? What about the second? What about the second and the third? This is going to be a little difficult to say that this can be plus, this can be minus, based on the way the neighbors I am selecting, what will be my output. Agreed? But if technically now, if I use a straight line function, mathematically, how do we use a straight line function? That y is equal to mx plus c. So in all the points which lie on the left side of this line, they all are known as plus. They all will come under the category of plus. And the data points, now all the points which are lying on the right side of the line, they will be all negative because most of the points are minus or the red points. Can I say that all the points which are lying on the left side are plus and all the points which are lying on the right side are negative? There are very few. There is only one plus sign, and if you see, all the points belong to the red negative class. One way I have to do something. But again, the question is, why this straight line? That how do I decide the straight line? So one point to understand is that when data points are given, that is known as a hypothesis space represented by capital H, and the line is represented by small h. Right? And it is going to be this red line which is going to divide the data points into two different classes. So they can be more than one solutions to a problem or infinite solutions. I can draw infinite straight lines. But which one to accept? The line which will be accepted is going to be one with gives me the minimum error. Right? The error word will be different for different algorithms, but I will accept that straight line which will give me the minimum error, or I can say the maximum accuracy. Clear? We will calculate, as I told you, in supervised learning, we keep the track how we can have maximum accuracy and minimum error. So what is the capital H over here? Hypothesis space is the set of all possible legal hypotheses. This is the set from which the machine learning algorithm would determine the best possible only one, which would best describe the target function. And small h is a hypothesis function that best describes the target in supervised learning algorithm. So now, technically, what does supervised learning mean? That the hypothesis or the small h, they can be several small h that an algorithm would come up, depends upon the data, also depends upon the restrictions bias that we have imposed on the data. So next thing is, we need to find out mathematical functions which give relationships between the data points, right? So basically now the idea is that we want to find a mathematical function where, we want the error to be minimum or the result to have maximum accuracy. Again, I am repeating, we want to find a simple mathematical function which gives me minimum error or maximum accuracy. Clear? Thank you, Atul. Thank you for your understanding. Thank you, learners. So now, what are the different stages that we are looking at? Now, suppose data points can be of any kind. So if this is my data points over here, and if I want to solve it with a simple linear function, see, straight line function is a simple mathematical form, calculation that y is equal to mx plus c. Okay. So when y is equal to mx plus c, right? And if these are my data points, now how do I calculate my error? This is going to be actual minus the predicted. It will have very high error. And this particular concept is known as underfitting. Do you think that this straight line is consistent covering all the data points? No. Right? So the simple straight line equation or function is not capable of covering all the data points. That is known as underfitting. Other way is that if I draw a function which passes through all the data points, so it makes it a very, very highly complicated mathematical function with high degree, right? So it makes a complicated function with high degree mathematical function. That also we don't want. Why we don't want? Because if the data point is out of all the data points, then this is going to give me my maximum error. So we want a mathematical function which is simple and which covers all my data points. So something like this exponential, right? And this gives me a good fit or a good balance. Now clear? So Ajay says no. So the model even fails to predict labels, what it learned, right? It will predict the labels, but with very low accuracy. The error will be high. So we will not accept models with high errors or low accuracy. So overfitting is a situation. How do I know the error is high? Overfitting. So one way is that error is equal to, if I talk in technical terms, so how do we know that if it is underfitting, overfitting? So that's what I'm telling you. Generally, the formula for error is bias square plus variance. What is it equal to? It is bias square plus variance. But the equation is in good balance, not linear. Yeah, it's not necessary that it has to be a linear equation. No. We want an equation which is simple and nice. So how do we know? So now if I say that error is equal to bias square plus variance over here, right? And this is, so how do I know whether it's overfitting or underfitting? It's not about the straight line, but when I have variance, if the variance of the data goes very high, then I know that it is an overfitting model. If the bias of my data goes very high, I know it's an underfitting model. And to keep my error low, I want the bias as well as variance to be low. Getting my point? Right? Now, what do we mean by bias and variance? A very, very typical example. A bias means how far are we away from the original data points. So bias means we are close to the center. Variance, what does variance mean? The spread of the data is also low. So this is the ideal situation we always want the data points to be in. This is where we will say, okay, a good fit has been achieved, where we have the low bias and low variance. Okay. and when we have the low bias, and when we have the high variance. Low bias means that the data points are near to my actual target points but spread out. So what is the case? Happens over here. This is known as the overfitting case. And what is high bias and low variance? That over here, these are my data points. And this is high bias. So this is underfitting situation. So in whole of machine learning, we don't want underfitting. We don't want overfitting. Of course, this is a worst case where the bias is more, variance is both. The idea is to have low bias as well as low variance. Clear? Okay. Now, I'll explain the previous example with this explanation after this, Puneet. I think so this will make things more clear. So these are my data points over here. A linear model is not a good fit, underfit. That means over here, what is more? My bias is more. What is bias? That my data points are very far away from the actual points. Bias means we are far away from the actual points, right? This is high bias. And what is variance? Variance is when the spread of the data is more, right? And when spread of the data is more or my mathematical function is too complex, then it is overfitting. When my mathematical function is too simple, it is underfitting. And when it is a balance, it gives me the right data. So now when I talk about complexity, now when I say overfitting means more complexity, that generally linear models give me underfitting, right? We start with simple models, but generally they do underfitting. Then we will move on to non-linear models, support vector machines, tree-based models, deep learning models. Why are we doing this? Because they give me more results, better results, more accurate result, less of error. But what is the cost? That my model has become complicated. I'm losing the interpretability of the model. What do I mean by interpretability? That if this is my input, right, how do I know that this is going to be my output? That's possible in linear model because I know y is equal to mx plus c, that if this is my input, I will get this output, otherwise I will not. Clear? And to make it more clear, the overall picture that I was talking about, please look at this slide. So ultimately, where is the trade-off? Where are we fighting in the whole of machine learning models? If life was so easier, wouldn't have the problems be solved by now? But no, there is still a trade-off which is going. So how will I know it is underfitting though it is showing in diagram? Is there any? Yes, they are mathematical way. But first, let's get the grasp of the thing, okay? That ultimately the idea is to get highest accuracy, right? And interpretability is also important. Why? Because we want to see why am I getting this output. So we always start with linear regression or logistic regression problems. That is what we do. That is what we are going to do in our whole of this journey. And why linear regression? Because they are linear and smooth, well-defined relationship, easier to compute. And as we move along this journey, decision trees provide good accuracy with high interpretability. KNN clustering. Clustering and KNN algorithm are mid-range. Interpretability is okay and accuracy is also okay. But if I want really good accurate results, that is why new algorithms, complex algorithms were built with kernel-based approach for support vector machines, ensemble methods, and of course, neural networks. Now clear? Is this slide getting clear to everybody? That is why complicated neural networks are capable of solving non-linear relationships, non-smooth relationships, and long computation time. Clear? Okay. If I want interpretability of the models, then I might go in for decision trees, but I will have to compromise on my accuracy. But if I am not interested in interpretability, that we are not, we always want best result. That is why neural networks, deep learning have taken the market. It is we as users who will decide. What is the difference between accuracy and interpretability? Interpretability is how am I going to find out the relationship of output given a particular input? So if I know a mathematical equation, okay, this is related with beta naught x1, beta 2 x1, I know why am I getting the result. But if it is some integratable model like neural networks working in layers, in different layers, in some layer differentiation, integration, addition, subtraction is happening, I will not be able to interpret the result, but it is giving me highest result, then of course I will use it. If I have a very mathematical complicated system. See, now try to understand the whole story again. Let me just repeat the story because this is very important in the whole of machine learning, and these concepts are valid for deep learning also. Okay. The story says that we want to predict the output or the data. We are clear? The first point says we want to predict the output of the data with minimum error or maximum accuracy. First 2 points are clear? The threshold, Simon, is maximum accuracy and minimum error. That point is clear, right? And which is the simplest mathematical function that we have? We always talk about a straight line. If that straight line is giving me minimum error, is it that only we will always apply one algorithm, or is it a different algorithms or a different hit and trial methods that we have to apply? It is different hit and trial methods, algorithm that we will try to get the output. It's not just, oh God, regression and decision tree is working. Okay, this is the end of it. No, you might go in for advanced algorithms, and that's where the research is going. Why do you think that the problems are not solved? Because every time, every algorithm will have its own pros and cons, and the research is going at each and every level. And it's still going, we are just trying to improve on the algorithms every time. Why? Because we still see the LLMs, the chat GPT giving us wrong answers, wrong predictions. So there is still a lot of scope of improvement, where we have to work. Clear? So life was, if the thing was so easy, I think so by now, everything would have been solved by AI and machine learning algorithm. No. Why is it not simple? First, data is variable, uncertain. It keeps on changing. Secondly, every algorithm has its pros and cons. So the errors, the accuracy, my requirements upon the product, on the data or the algorithm keeps on changing. And that is why this change happens. Right? So they are plethora of algorithms which have been built. As in machine learning, we will always start with linear regression algorithms because of the simple mathematical function and high interpretability, but they have minimum accuracy. But as we move along with the journey of decision trees, clustering, kernel based, we want maximum accuracy, but the trade-off is that we decrease on the interpretability of the model, right? So as I have been telling you, splitting the data for machine learning in supervised learning, we always and always want to select the data randomly. So there is a function train underscore test underscore split that we would be using to split the data. Train underscore test underscore split, which is part of the Scikit-learn library. This is my data. And we will be randomly selecting it and dividing into training and testing data. Now clear? And most of you see this is around 70 to 80% of the data. And this is around 30 to 20% of the data. Puneet is just wondering if interpretability is more important as we go to complex problems. Not really. Not really, ultimately, Puneet, not really, because we are always interested in the final result. It's something like, as I give my example, suppose, you have a magician and, the magician turns a pigeon into a flower. Are we interested how does it does, or are we interested in the output as a flower? Okay. So we are always interested in the output. Got it now? Better? Yeah. So if logistic regression is having minimum accuracy, then it is a no, Nanda. No. The accuracy is less over here. It doesn't mean that it's a wrong prediction. Logistic regression might not give you the best results for the prediction, and maybe using a neural network would give you, it's something like, using logistic regression is giving you 70% of accuracy, and neural network is giving you 97%. So that's the difference. But of course, neural networks are better. That means, right? Got it? So yeah, there are a lot of terms which you have to be associated. You have to understand it in the correct sense. I understand I'm giving you time for doing that. Yeah, now coming on to the part that you all are interested that, ma'am, what is the mathematical equation? How do we know the mathematical term which is used to see the output? Now, first of all, we are going to calculate error, right? In regression, the error is known as mean square error. Now, let's start understanding this. So we have this mean square error, okay? The error name is that I'll explain you technically when we move on to regression. Now, in supervised learning, whether it's classification or regression, we know the data is divided into training and testing. Now, tell me which error is more important. Now, let me put it in this way, that you go to a class, and you are pursuing some course, you do errors, you are learning, and you do errors while training, right? And still you don't perform well in the test. And there is somebody who doesn't attend even one single class and performs well in the test. So which error is more important? It is the training error which is important, or the testing error? Among the two. Of course, both are important, but among the two, which one is important? So what is more important, to have the training error less or the testing error less? The training error is less, but the testing error is very high. Is it a good thing? It's an even big failure. So again, I'm asking you this question. Is the training error important or the testing error important? Of course, the final test, if you're not performing well on the final day of the test, then the whole training is useless. Agreed? So when my training MSC is high, of course, I can reduce my training by giving in more data, and my testing MSC is less. What is this case? This is the case of underfitting. Of course, the training error should not be high than the testing MSC. The model is too simple for it to solve, and then I will say the model is underfitting. Now clear? That was the question, I think so. So now clear mathematically. So this is how I will judge based on my training and testing that my model is underfitting. So I will now not use a straight line to solve my data points. I will not use. Okay. Other is my training MSC is 0. Excellent. But my testing MSC is so high. Absolutely not acceptable case. So this is the case of overfitting, which is high variance. And what do you think the data or the model goes through? Is it more of underfitting problem or an overfitting problem? What do you think? most of the models in machine learning face which kind of problem? Reducing the training error is easy, but failing on the testing is a total failure, and that is what we will look at most of the algorithms, that how to prevent overfitting in the models. That is why I was telling you these concepts are very, very common to machine learning, deep learning models. So are you getting a grasp of it? And I don't straight away start with regression. Come on, let's start doing it, other things. You have to have good foundation of machine learning concepts, so that you understand other materials, the in-depth knowledge, how we accept and reject the particular model. Training and testing, that we will decide, because when the data is there, we will split the data into training and testing, and then we will calculate the training error separately and the testing error separately. Okay, we will have suppose I said 1000 rows, 700 rows will be used for training. Then we will have 300 rows used for testing. Then calculate the errors for training and testing separately, and then decide whether it's underfitting or overfitting. So what will be the best case? Where my training error is also low, testing error is also low, or almost equal to each other. So again, looking at the concept x-axis, we have the model complexity, and then we have the predictive error. So over here on the x-axis, this is my underfitting over here. And if what is overfitting? That when I start with my model, simple model, my errors are high, both the bias and both the test and as well as the training. As my training increases, the training error or the model complexity increases, the training error decreases, but the test error will dip and then increase because of high variance. So we want to find out a model. How do I decide which model is best for my data? Where the training and the testing error are minimum or close to each other. So this is what I'm trying to explain you. Please try to understand that as the model complexity is less, here we have the bias more. As the complexity increases, the bias decreases. When the interpretability is high, the variance is low, and as the complexity increases, the variance increases. But we are looking at a point where these two intersect to find the optimal model complexity. The variance is the spread of the data. Variance is a statistical term which means the spread of the data. So as my model complexity is going to increase, the complexity, as the complexity of the model increases, the variance or the spread of the data also increases. Got it? That's the relationship. Again, I am telling you, we are trying to create a graph between error or accuracy is going to be opposite of this, and this is my model complexity. We always start with minimum complex model. This is the case of underfitting. Agreed? When my model is simple, but my bias is high, as the complexity of the model increases, my bias decreases, but my variance increases. So I don't want the overfitting situation or the underfitting situation. I am looking at a situation where my error is minimum. So the test error is U-shaped in curve, and where the value is minimum, that becomes my optimal model complexity. Now clear to everyone? Okay. Now since the topic has been taken, now let's do one thing. If you have downloaded the ebooks material, so I want everybody to make a folder in the desktop and move under lesson number 3. Something like this. See, what I would see is, let me share my screen. In work and data break, how do I understand that? So once you are into, now we're starting with lesson number 3. So do you see this 3.1 and 3.2? learners? So how do you go about opening it? Open the Jupyter notebook environments, install and open the file along with me. So chapter number 3, we have to start with lesson 3. Lesson 3, supervised learning, regression and its application. Yeah, are we all able to open this? Let me guide them that how do we go about it. See, the prerequisite for the course I've been telling it is Python. So we always, like there are a lot of tools like PyCharm, VS Code, you can do it through other tools. But generally we use Anaconda Navigator download. Please go ahead and go to the Anaconda, fill in your like the details, the email ID, and I want everybody to download the Anaconda, right? And based on your system, whether it's Mac, Linux, or Windows, and go in for a full distribution. Don't go for mini Conda. Google Colab. If you're aware about Google Colab, that's also one of the online tools available, which helps you to run the code in the Jupyter kind of environment. Let me show it to you. Anaconda distribution, go and download it, install it. Or the other one is go to Google Colab over here. Just log in through your Google account. That's the another way to go about it. And from here, I will upload the file. Which file? The file which I have already downloaded on my ebooks. That's there on my desktop. Machine learning. Third chapter, 3.1. And I open it. Yeah. So there are 2, 3 methods, whichever one you are comfortable with. That's not an issue. If you're clear, you're comfortable, Anush, on VS Code, that's not an issue. Got it now? Everybody is there with me now. So this is one of the very safest tool. You don't need to, download the Anaconda on your desktop through the Google Colab, through your good internet connection, you will be able to run the code. Yeah, so this particular file is, basically if I talk about 3.1, again, I'm repeating, go on to your learning management system on the reference material. Please download the ebooks, the Jupyter notebooks, and then try to open. So if we talk about, if we are back to 3.1, let's quickly go through the file. That file is completely theoretical. Okay, nothing great in that file. It talks about what supervised learning is and what are the 2 types of algorithms in supervised learning. It's regression and classification. What is the difference between regression and classification in supervised learning? In regression, the output is always numeric. And classification, output is always categorical. So when the target variable is categorical, we do classification. So this example, we are very clear. So when it's predicting numerical value, right, that is regression. When we are predicting a categorical outcome, determining the whether tomorrow it is going to be hot or cold, visualization, the same thermometer scale divided into 2 colored regions, gold and red for hot, with the threshold separating is classification. And if you look at the applications of supervised learning, do you think HR people use machine learning to identify the different job profiles, shortlisting of the resumes? HR is also using machine learning now. Yeah. In finance, what is the use of machine learning in predicting of fraudulent data? Are you ready for that loan approval or not, right? And this is similar to how a credit card company determines your credit worthiness before issuing a card. Then emails, this is about spam filtering, whether it's a spam or not. Manufacturing, anybody in manufacturing? So in manufacturing, supervised learning is also used to inspect the quality, classify the products into different grades. For example, a factory might use a machine learning model to check for defects in products and ensure they meet quality standards, much like the quality control inspector. Maritime industry, It helps in forecasting the historical events, weather condition. So precautionary accident, it's capable of predicting any kind of, weather. It might get wrong also, which we have seen. And supervised learning techniques like regression model can be used to predict tidal currents, forecast demand and supply, reducing inventory losses. Think of it as how weather forecast predicts rain based on past weather patterns. Fraud predictions, we use this in agriculture field too. I'm into automating parking. So under supervised algorithm, there are a lot of algorithms that we will begin tomorrow. Tomorrow, again, as you understand my style, we'll start with regression, then linear regression, logistic, naive bias, KNN under classification. They all come under classification. So under linear regression, we would be working on multiple linear regression. And before we move on to classification, there are a lot of concepts that we will study, such as, excuse me, cross-validation, regularization, hyperparameter tuning, Scikit-learn pipelines. So there is a lot more to be explored tomorrow. We will be concentrating on linear regression and its concepts tomorrow, right? And linear regression is now very clear where the output is numerical, then like predicting housing pricing, we will use regression. After doing supervised regression in supervised learning, then we will move on to classification algorithm. Under classification, plethora of algorithms that need to be done. Initially, we'll start with logistic regression, naive bias, KNN, decision trees, random forest, and support vector machines. So it's a long journey. Tomorrow we'll do linear regression. Next weekend we will be doing classification. And then we will move on to the next stages of ensemble learning. Then it is unsupervised learning, right? So I think so you all are excited about this journey. So it's a long journey. I don't want to burden you today with all the concepts. So let's go slow and steady. That's my rule. Slow and steady wins the race. But I hope you got the crux of today's class, right? So this is 3.1, right? And we'll be beginning with 3.2. We started with the very first session of machine learning, where we understood what machine learning is, what are the different types of learning techniques, what are the different types of machine learning techniques, supervised learning, unsupervised learning, and reinforcement learning. What is supervised learning? Supervised learning means it consists of label data, which consists of input and output. We split calculate the errors. The two main algorithms under supervised learning are regression and classification. Then we understood unsupervised learning. Unsupervised learning consists of unlabeled data where based on the similarity of the data, the groups and clusters are formed. So two main algorithms are clustering and association. And last but not the least is reinforcement learning that based on the feedback, positive and negative, the machine learns. Are we good to go? Everybody is clear with these concepts of machine learning, the basic concepts? And then we started with the concepts of overfitting, underfitting, and a good fit. Yes, learners, now you will tell me what do we mean by underfitting, fitting in machine learning. Very, very important question. It will definitely be asked if you say that you know the concept of underfitting and overfitting. Yes, learners. Can you tell me what do we mean by underfitting and overfitting? Underfitting is the case where the error is high. What error is high? Bias is high. We are very far from the actual data point, but we talk about simple mathematical function. What is the advantage of simple mathematical function? That it gives us more interpretability of the model. What do we mean by more interpretability? That it gives the relationship between the output. And if we talk about overfitting, again, the error becomes high because the variance goes very high, right? And definitely it makes more and more complex. So we don't want a algorithm to be or model to be underfitted or overfitted. We want a good balance fit. That is, how do we judge that? That the training error and the testing error should be similar, right? So So today we will start with the first, learning technique, that is supervised learning technique and the regression model. Are we good to go? So as now you are getting more familiar with my style, first we will try to cover the concepts and then move on to the practical aspect. Because unless and until you clarity of what is happening, how are we going to interpret the model, there is no point moving on to the code. But definitely we'll move on to the code. But let's start with the concept of regression. So here we go with the regression. So what is regression? Now, if I ask you, what is regression? Tell me. So when we're talking about regression, learners, please be clear with this concept that always the target variable or the dependent variable are all numeric values or continuous value. Don't say the term data, right? See, everything is data, but if you're not very specific, and technically you go very wrong, right? So you have to understand now data. We're talking about structured data which in tabular form. It consists of input as well as output values, right? Whatever are the input or the output value, X over here is referring to your independent variables, right? But whenever we are choosing any model or algorithm, we always and always take into consideration the dependent variable. So it is very important that the dependent variable has to be numerical or continuous, right? So we are trying to find out. So basically, what are we trying to find out? We are trying to find out the relationship between the independent variable based on the output. Clear? So let's try to break the term linear and regression. Linear, we understand from simple mathematics that anything of degree 1, any function which has value 1 is said to be linear. So this means that progressing from one stage to another in a single series of steps, sequential extending along a straight line or nearly a straight line. So we all understand the term linear, right? And as very rightly said by Nanda, regression is a statistical terminology which is used to find out the relationship between one dependent variable. We always have one output. If the output is categorical, we will go in for classification algorithm. And if the outputs are continuous or numerical, we will go in for linear, not linear, but regression algorithms. So moving ahead, thus a linear regression means a linear approach from, so when I combine the two terms, linear regression, it means that the linear approach for modeling the relationship between the dependent and independent quantitative variables, it will plot a straight line because that's the simplest linear approach as a best fit along the data points to predict the target value, right? So, what are the different types of linear regression available to us? So, a simple linear regression is with one obviously the dependent variable is always one. That's the target or the output. But if the independent variable is one, it is simple linear regression and it is always represented by a straight line. So beta naught is the intercept and this refers to the slope. So this refers to beta naught plus beta 1 x1. Getting my point? And then we have multiple linear regression. That is over here when an independent variable, then this straight line turns into a hyperplane. So line in higher dimension, 2 dimension becomes a plane, and in higher dimension, it becomes a hyperplane. Getting my point? Are you all getting the concept, mathematical equation along with the graphical view? And of course, with the code. I'm trying to explain you from all aspects. All right. And when I say polynomial, sure, Hardik, I can do that. Right. Over here, we are talking about linear regression. Linear means something of degree 1. So do you see all the variables have, all the coefficients have the degree 1? Do you see this? Right? These are known as the regression. So the term linear regression means we are trying to find out relationship between the independent variables with the dependent variable. So a simple linear regression is beta naught plus beta 1 x1. Clear? That is when we have one input variable and one output variable. Mathematically, it is represented by a straight line where beta naught represents the intercept of the line and the beta naught represents the intercept and beta 1 represents the slope of the line. Clear? Have multiple linear regression, graphically, a straight line now becomes a hyperplane. That is a multiple linear regression. Of course, generally, practically, we will have more than one independent variables with output variables. And then we have polynomial linear regression. That is y is equal to beta naught, beta 1 x1, beta 1 x square, and q. Clear now? So now let's try to understand it from now, the same thing from the machine learning point of view. So in simple terms, it is a method of finding a best straight line fitting the given data set. So in simple terms, find a simple straight line which tries to find the relationship between the independent and the dependent variable. And best linear relationship, how do I decide the term best? Something with minimum error or maximum accuracy, right? Something with minimum error or maximum accuracy is taken in terms of simple terms. And if I talk about technical terms, it is a supervised machine learning algorithm that finds the best fit relationship on the given data set between independent and dependent variable, almost the same thing. But the basic concept or the algorithm it works on it is OLS, the ordinary least square method, also known as the sum of the square residuals. Clear? So to explain these terms graphically, mathematically, I want everybody to concentrate here on the graph or the slide shared. So this is an equation of a straight line. What is beta naught? Beta naught is the intercept. What do I mean by intercept? What is the value of y when x is equal to 0? Are you all getting this point? What does the term intercept mean? That what is the value of y when x is equal to 0? Clear? Is this point getting clear to everyone? And if I talk about beta 1 refers to the slope of line. Is this term getting clear to everybody? Since I have only one input variable or independent variable, it represents a straight line. Clear? Now, once we have understood the equation of the straight line, what do these blue dots represent? The actual data points available, right? That the first data point has value 1, y is equal to 3. This is value 4 and value is equal to 6. All right. Now, this is where how we are going to calculate the error. What is the error? The actual value. This you can consider this yi as my actual value, and the red dot on the straight line is the predicted value if I want to fit a straight line on these data points, right? So this is my actual output and this is my predicted output. Clear? The error is clear. How are we calculating the error? Now, what algorithm are we technically using over here? Ordinary least square method or the residual. Residual means the error sum of square error. So what does this mean? It is equal to the sum of the square of error, which is actual minus predicted value. Getting my point? So, and why are we taking the square of the error? There is a story behind that also. Why? Because suppose is plus 2, for example, and this error is minus 2. So the total error is 0. So what I'm trying to say is if the error is plus over here and minus, and if I add them, it will show me 0 error. It is not 0 error. So I will try to take the square of the value. It will become 4 plus 4, that is the error is equal to 8. So always the errors are taken as square of errors, and we are looking at minimum square of errors. That is why it is known as the ordinary least square method. We want the sum of the square error to be the least. This is known as the RSS. Getting my point, learners? So this is the total RSS. Why the total? For this particular data point, this is going to be my first error. For this data point, my second error. For the third one, fourth one, fifth one. And if they are infinite points, then infinite data points are calculated. Clear to everybody? So why? Okay. Now, because this is my actual y1, and what is my predicted y1? This is my predicted value, right? Base, because we are using Nanda, this particular function, this is my predicted value, and predicted values are represented as y cap. So for the first one, it will become beta naught minus beta 1 x1, then y2 beta naught beta 1 x2 for each data points. Now clear? This is how, based on this mathematical function, I am going to predict my output for each data points. Clear? So the formal statement of simple linear regression. I'm talking about simple linear regression with one input and one output. Y1 is the value of the response variable. Again, predict, target, predicted, dependent, they all mean the same thing. Do not get confused with the terminologies. In the ith trial, beta naught and beta 1 are the parameters. Xi is the value of the predictor variable in the ith trial, and epsilon I is the random error with mean E. Epsilon I is equal to 0 and variance is equal to square. Clear? Okay. Now this random error, this is very, very important to understand that a random error, we are talking about, are we talking about the whole data set or a part of data set or a sample of data set over here? This is my population, and if I take a part of it for training and as well as testing, do I always consider the whole data set or a part of data set? It's always sample. And is my sample, and we want the sample to be the true representative of the population. But since it is a part of the data, there will be some error also associated with it, which is irreducible, that is represented by epsilon, right? So epsilon I is the random error with mean. This is the random error which is always going to be introduced. It's not reducible like bias and variance or overfitting, but it's part of the whole linear regression where the mean of that error is equal to 0 and the variance is equal to epsilon square. Now clear? So the idea of whole linear regression or significance model is that it is highly interpretable. What is the idea behind this? That it is why the error is 0. We always want the error to be 0. In this case, we are considering that, the average of the error, not the square. The sum of the square or the average of the error is equal to 0, not the square. Okay. So now the significance of linear regression lies in the fact that we can easily interpret and understand the marginal changes with with input to the output. So linear regression is an highly interpretable model. How is it interpretable? That if we increase the value of x1 by 1 unit, keeping the other variables constant, then the total increase in the value of y will be beta 1, and the intercept term beta naught is the response when all the predictor terms are set to 0 and are not considered. Right? So how much is my y value change will depend on how much is my beta 1, is it positive or negative, beta 2 and beta n. So now, what are we trying to find out in linear regression? The values of beta naught, beta 1 and beta n, right? Where the error is minimum. Clear? Right? I understand, there are a lot of concepts, a lot of mathematical terms coming. So just hold on till we start moving on to the practical part, and, you will see them practically. Just try to grasp as much concepts as you can. So different assumptions which we follow in linear regression is linearity. That is the relationship between the features and the target. Homoscedasticity, the error term has, this is where, the linear regression has its assumption or constraint, and the term is known as homoscedasticity, that the error term is constant variance throughout the whole data. The error term will be constant. Multicollinearity, there is no multicollinearity between the features. And if we talk about independence, observations are independent of each other. Getting my point? Normality, this is where the point I was saying, that the error residuals follow normal standard distribution, where mean is equal to 0 and the standard deviation is equal to 1. Okay, so multicollinearity means that we can have more than one input. Are they related with each other? No. Every first input should be independent with the second one should be independent with the third. The input should not be dependent on each other. They should all be directly dependent on the output. First, let's try to understand the concept. So how do we go about in the supervised learning process? That we have this full data set, right? And we will, after doing all the pre-processing, so today I told you to revise all your EDA, that we will load the data set using pd.read_csv command, do head and tail, try to find out null values, work on them, do encoding if required, and then split the data into training and testing. First step is getting clear. And of course, training can be, it's generally 7 to 80. If you want to keep it 50-50 also, nobody is stopping you. Or 60-40, that's completely up to you. Okay. And the function which is used in Python in the Scikit-learn preprocessing library is train_test_split. X is the first parameter which represents the features of the input data. So this is how we will create a list or an array which will contain all the input. Y refers to the target or the label vector of the input data. Size of the test data, test_size. And finally, we have random_state. What is this random_state? It is the seed that initializes the pseudo-random number generator. What does that mean? That I will give any fixed number. It could be 42, it could be 3, it could be 0, it could be 500, right? I want to keep this number constant so that the shuffling or the randomization of the data happens in the same way, so that I can check the accuracy and do the comparisons. Clear? Right? So again, remember this point. Whenever data is given to you, you have to identify it in terms or split it in terms first, in terms in number of inputs and the output. Always separate the outputs from the input, and Then we will use this function and then we will get 4 outputs. Train underscore test underscore split gives 4 output, that is x underscore train, y underscore train, x underscore test, and y underscore test. Clear? Training underscore test underscore split is used to split the data, right? We are preparing the data which will be used for training and testing separately. So the parameters of this function are input, output, how much we want to give for testing. It could be 3/4, half, completely up to you, no rules for that. And random underscore state gives me the seed that initializes or does the shuffling of the data in the same manner. And the output of this function is 4 output. I get input training and output training data and input training and output testing data. Clear? And now if I talk about multiple linear regression, right? In 3-dimensional setting with 2 predictors, 1 response, the least square regression line becomes a plane. So this is a multiple linear regression model. Epsilon is the normalized error, okay, which is irreducible. Nothing can be done much about it. And now we will practically deal with data which has 3 inputs: the budget of TV, budget of radio, budget of newspaper, and which one of them affects the sales most. So this is the first, algorithm that we are going to study. Okay. So this is simple, this is polynomial, and these are the errors. So let's start with the practical work and then get back to the different errors and analysis. Got it? Have you got an idea what linear regression is all about? So I request you all learners to, from the LMS, to open 3.2 supervised learning regression, linear regression file. Okay. So now, do you understand the term independent variables, straight line? When we have in 2-dimensional, when we have 1 input, 1 output, it's a straight line. Blue dots are my data points, and this is a straight line or the line of regression, which I want to fit on the data points. This graph is now very clear to everybody. I'm starting with the file now. The first 3.2 regression, this graph is clear. And where do you think regression is used? It has a huge application in oil and gas industry. Various types of data are collected in oil and gas industry, from surface, subsurface, to understand production, sale processes, how much gas is required, how much liquid, how much is the pressure that needs to be created. So linear, non-linear regression model forecast global oil production. Oh my God, the whole world is fighting on oil, and well, we can use our regression models to forecast the global oil production, right? So the whole world is on a big fight on oil only, right? Marketing, linear regression helps to analyze the effectiveness of advertising campaigns, predict sales based on marketing spend, segment customer based on demographic data, right? Then we have retail. Then we have linear regression is utilized in retail for demand forecasting, inventory management, pricing optimization, and customer analytics. Healthcare, linear regression is applied in healthcare for predicting the patient outcomes, analyzing relationship between the different medical variables and their diseases. Getting my point? And finally, we have the real estate, that in the real estate industry, linear regression predicts the property prices based on the factors such as location, size, amenities, and economic indicators. Clear? So now what are the different types of regression? Regression can be classified into 2 categories, linear and non-linear. Linear regression finds a straight line relationship between the dependent variable and one or more independent variable. Non-linear regression finds a relationship between the dependent variable and independent variable using a curve or more complex shape. Okay, so getting back to linear regression, it is, so technically if somebody asks you what is linear regression, in machine learning, you will say it's a supervised learning algorithm which is used to, please try to understand each and every term, is used to predict a continuous target variable. Please be clear. It's not continuous data, as you all were saying. That's a wrong statement. It helps us to predict continuous output variable by modeling its relationship with one or more independent variables through a linear regression. It predicts a continuous dependent variable based on one or more independent variables. So it predicts the continuous dependent variable. Here it says target, output, dependent, completely anything you can say. It uses the least square criteria to estimate the coefficients of the regression equation. What do we mean by the least square criteria? That the value between the actual and the predicted value, the square of the error of this error, that is RSS, should be minimum. That is the residual sum of squares. Getting my point? And it can be applied if there is linear relationship between the variables. So in case the dependent variable is continuous and independent variables can be continuous or discrete. We are not bothered about our input variables. So for predicting the output, we are always considered about the output. So the relationship between a dependent variable y and one more independent variable x is established using a best fit straight line, which is also known as the regression line. And there are two types of linear regression. One is known as the simple linear regression. Other one is known as the multiple linear regression. All right. So simple linear regression is clear to everybody. We have one independent variable and one dependent variable. Do we understand now the terms beta naught and beta 1? This is the intercept and the slope. Yes, everybody is understanding now what is simple linear regression. And as I told you, a simple linear relationship is given by one of the input, that is TV expenses over here as my input. And in the output, we have that sales. That means in this particular data set, we are trying to establish the relationship that if what is going to be the budget of TV and how it is affecting my sales. So what do you conclude? Do you see the red points? These are the predicted values and the blue points are nothing but my actual data points, and I'm going to calculate. It automatically does the calculation of the error if once I apply the algorithm. Clear? So do you see a kind of positive linear relationship? Can I conclude that this shows a little positive linear relationship? That is, the value of TV expenses increase, the sales is also increasing. It shows a positive relationship between them. Getting my point? And practically, if you look at the real world problems, they will not be simple linear regression problem. They will going to be, multiple linear regression problem. There will be more than one input. From how we know positive and negative? See, positive and negative, Basant, that's shows it very clearly from the graph. If the graph is showing this thing, that as my x is increasing, y is also increasing, it shows a positive relationship. See over here. And if x is decreasing, y is also decreasing. But if my graph is like this, what does it show? That x increases, y decreases. And if x decreases, y increases. Getting my point? So this is a negative relationship, inverse relationship between input and output shows negative relationship, and direct relationship between input and output shows positive relationship. So as I was telling you, practically, if I talk about real-time data, we have more than one inputs and output. So multiple linear regression models the relationship between the two and more independent variables, predictors, features, and the dependent variable as a straight line. The equation for multiple linear regression is y is equal to beta naught plus beta 1 x1, beta 2 x2, and beta n xn. That x1, x2, xn are the predictor variables, and beta 1, beta 2, beta n are the coefficients of each predictor. So let's start practically working on this data set. That this becomes now, if I want to try to find out the relationship between TV expenses, radio expenses, and sales, so now my straight line turns into this hyperplane. Do you see the difference? How the straight line has got converted into hyperplane? And of course, there is one constraint that we cannot view more than 2D or 3D graphs, right? We cannot view more than 2D or 3D graphs, right? That correlation covariance is same as regression, but in regression it's a linear relationship, but the positive and negative relationship is the concept same as correlation and covariance. That correlation and covariance is founded by Pearson's coefficient of correlation, but here we are talking in terms of linear equation. But if I talk about one input x1 and y, how x1 is related to y, then that is r. That is this +1 -1. That exactly is the same concept. The concept is not very different. Linear regression is using that particular concept. All right. So now let's start practically working on the data set. So what I want everybody to do is on your, go from data set folder, open your Jupyter notebooks and keep the TV marketing.csv data in the same folder where you have kept this 3.2. Yes, learners, wherever you have kept this 3.2, keep the TV marketing.csv, copy it from the dataset folder and start uploading this data. Clear? And then run this thing. So basically, this data set consists of 3 input variables. This is my x1, x2, x3, and this is my output. All right. So once I have done my head, what does the head command do? What does the head command do, learners? What does it prints? The top 5 rows by default, and these are my inputs, right? And what does the info function do? Good, Rishi. Good, Anush. What does the info do? It tells me there are no null values in this data set. And of course, unnamed is not required over here. And all other, my inputs are also in numerical value. And what is my output? My output is sales, and that's a numerical value. And that is why regression will be used. Clear? And that is why regression will be used. Getting my point? Okay. So what is the first thing that we are going to do? Since this data does not require pre-processing, it's a clean data, so nothing required to clean or check on the null values, etc., right? So we are considering the data to be clean. So now when I want to fit any model, what is the first step that I will do? I will try to separate the input with the output columns. Agreed? The first step is to extract the features of the data set and output. What is this ILOC in Python code? Index-based filtering. So if I see very closely that 1, 2, 3 are my input index, this is of actually no relevance. This is of no relevance. These are my input values. And this is my output value. Clear? So in this case, ILOC, the first colon represents, it talks about all the rows, but only the columns which are there, it says 1 and 2. So how many inputs are we talking about? Only the first one. Only the first one is TV. And what is the output? Only the sales. This point is getting clear. What are we taking over here? We are talking about TV and sales. So we are trying to implement linear regression, right? We are trying to do simple linear regression. This X and Y is clear. I've only taken a part of it. First, I've taken one input and then I'll take all the three inputs. This point is clear, right? And then we have the from Scikit-learn model selection import train underscores test underscore split. And now I am taking my input, that is only the TV input. Y is my sales. Test size, 30% of the data is used for testing, and random underscore state is taken to be 42. 42 is generally considered from a fiction that it's considered to be a good number for the whole universe. Clear? Okay, so now what are the different steps to now fit the model? Not much of coding. That's why Python is a preferred language, beautiful language. That is from sklearn.linear model import linear regression. That is, first we will import the library. That is, sklearn is the main library and we are importing linear regression from there. So when I imply linear regression, it is lin underscore reg, and this is fitting. That is the training input and output training data. Getting my point? Fit function is used to fit the data or train the data. What do we mean by train the data? Finding the parameters over here, that is beta naught, beta 1, beta 2, beta 3, etc. Clear? Are you all there with me till this code? Anybody who's still facing any difficulty, who's not been able to run this part of the code? Till here, are we good to go? First step is to import the library which contains the linear regression model. And then I will create an instance of this linear regression function, right? That is lin underscore rig. It is a instance. What do you understand by instance? Object of this particular function. And then fit the training input and output data. It is divided by using this train underscore test underscore split. And we get these four outputs. Input training and testing, output training and testing. I explained you train underscore test split, where we get the four outputs. Now let's try to find out the linear relationship between the sales and the TV. So TV and sales. So we want it to be an input. So if you visualize the linear regression model, X label, we don't want it to be, I think so that's a little opposite of it over here. This is TV change, make changes in the code, and output is sales. How do we delineate contributing and constraining factors in model? What do we mean by that? Huyan, delineate, what do we mean by that? Okay. So what does this graph represent? What does this graph represent? This plot shows a positive linear relationship between sales and TV, and where the blue regression line indicates the model's prediction. The green data points are generally close to the line suggesting the model fits the data reasonably well, though some variability exists. Right? So does it show a positive relationship, Basant? Right? Do we see that there is a positive relationship between TV and sales? No, it's not the trained data. It is the test data. Why test data? Because I'm plotting input as training and predicting the output. The x-axis is the input. The x is input, right? And the output is prediction of the training. Right? So we are trying to plot over here. Plot over here is the straight line. Right? But why am I saying the test data? Because actual data points are my input and output test data. Now clear? We are trying to do a scatter plot over here. Scatter plot is between input and output test data. The actual data points are my testing data points. Okay. And the plot, the straight line is input training and predicting the output. That is why it says the linear regression model for test data set. Now clear? So what do we conclude from this graph? We can conclude that the plot shows a positive linear relationship between sales and TV, where the blue regression line indicates the model's predictions. The green data points are generally close to the line, suggesting the model fits the data reasonably well, though some variability exists. Okay, so this shows a positive relationship. Now, the important point is, how do I understand? Is this model underfitting or overfitting? So, when we are developing machine model, what is the most important point, important concept that needs to be taken into account? The concept of overfitting and underfitting. So when developing machine learning models, achieving the right balance between the complexity and simplicity is crucial. What are the points of overfitting? Let's quickly go through that. Overfitting occurs when the model learns the noise and details in the training data too well, to the extent that it is negatively impacts the performance on unseen data, right? That means when the variance is high, sign high accuracy on the training data, but poor accuracy on the test data. So how do I know that my model has overfitted? That I get a good score for training data, but a bad score for testing data. And why is it? What is the reason? Because the model is too complex. It has got too many parameters. Underfitting happens when the model is too simple to capture the underlying pattern. Poor accuracy on both training and testing data. Underfitting is more easily to detect, but overfitting is a constraining problem. So what are we looking? How do we solve this problem? We want a bias and variance trade-off. Bias error due to overly simplistic assumptions in the learning algorithm. And high bias always causes underfitting. Variance is error due to excessive complexity in the learning algorithm. High variance causes overfitting. Clear? So low bias, high variance, again, it is failing to be a good fit. This refers to overfitting. High bias, low variance, it leads to underfitting. And optimal trade-off, finding a balance between the model performance on both training and test data. So this is what we are actually trying to achieve in the output, right? So just to understand things, you have to understand the machine learning model from the mathematical intuitive behind it. If it is possible to understand it graphically, well and good, because in higher complexity, higher dimensional plane, it becomes difficult to access, to understand it visually. But mathematical intuition, the concept, and how do I interpret the results? Are you understanding? And of course, how we are implementing those functions in Python. That is where, your concentration should be. Mathematical concept, or what is the concept of that particular algorithm? How are we implementing in Python? And how am I interpreting the results? That should be the option. Clear? Is this point getting clear to everybody? And how do I check the error? The checking of the error is going to be through the training and testing error. So if you just look at this, I'll tell you what these errors are. So if you just look at the training, error is more than the testing error. So is it underfitting or overfitting? Definitely underfitting. Consider increasing model complexity. That means linear regression or a straight line fit is not a good fit on this particular data set. Agreed? So now getting back to the concepts of errors, how do I evaluate my regression model? Okay, till here, are we clear? Okay, so one of the simplest error is known as the mean square error. This is nothing but your RSS, the residual sum of square error. Please try to understand. This is nothing. So errors, do you think one error is easy to define linear regression? No, right? There would be several errors. So now let's try to understand different errors available in the linear regression model. Yeah. So if I talk about the mean square error, this is nothing but my RSS or the residual actual minus predicted value, the whole square. So error, square of the error, and if I take the average of it, it becomes mean square error. Agreed? Are you understanding this error? And when I talk about root mean square error, that is when I take the under root, square root of this particular MSC. But what is the need of taking the root mean? Can anybody tell me? What is the need of taking the root of this mean square error? Anybody who can explain? This is exactly the same, question which relates to standard deviation and variance. Anybody who understands the relationship between standard deviation and variance? Anybody who understands the relationship? After square error will increase, so square root will get proper value. No, Nanda, that's wrong answer. Yes, ma'am, rooting variance is standard deviation. Like, but why do we take that under root? That's the question. Why do we take this under root of variance? What is why? What is the significance? No, it doesn't mean that squaring will get a proper value. No, no, square root will. Yeah, because ultimately we have to compare with other values such as average. So average is a simple value. Simple values cannot be compared with a squared value. Mean square value cannot be used for comparison with other values. So to make it at, it's something like, can I compare a centimeter square, the unit of area that is equal to centimeter square, with centimeter? Can I compare a centimeter square or a meter square, a unit of area, with normal meter? No, that goes mathematically wrong. So just by taking the square root of MSC, now it becomes at the same level, and then the comparison can be done. Yes, and if we talk about mean absolute error, that is actual minus the predicted value, and this is I divided by n, I get the mean absolute error. Clear? Now, these are all, we can say absolute terms of error. And if I want to do comparison between different models, now what difference does it make if I'm saying actual minus the predicted, the whole square? And then I say predicted minus actual, the whole square. Is there any difference between that? Is there any difference? No. So mathematically, whatever way they write, the answer will be same. Clear now? Now let's understand another factor of comparison, that is R square. Please try to understand R square. Okay. Okay, now to understand R square, it is a relationship between SSTO. What is this? Total sum of square. These are my actual points, and total sum of square is the difference or the total variation between the actual points and the average. Generally, we want to always find out how far my points are from the average, right? How my points are far from the average, right? So SSTO is getting clear to everybody. So over here, this is my actual data point, and here I'm doing my comparison. Is the total sum of square clear to everybody? What is SSC? Is SSC same as the RSS? Yes. Here we are trying to find out the difference between actual value and its difference with the average. Yi minus y cap b square. Again y square, because I don't want no positive and negative values cancelling each other. Clear? And if I talk about SSC or the error sum of square, this is like RSS, actual minus the predicted value. This is my actual, this is the predicted value. Do you see this? So the uncertainty of the data around Y observations lie around the regression line. If SSC, all observations fall on regression line, larger the SSC, the greater is variation of the Y observation around the regression line. Then we have regression sum of the squares, right? This is actual, the average predicted value with the difference with the average. So the difference between the predicted or the fitted value on the regression line and the mean of the fitted value, that is equal to SSR. The measure of variability of Y's associated with the regression line. Larger the SSR in the relation to SSTO, greater the effect, right? So if we look at now the whole picture, that my total sum of the square is equal to SSC plus SSR. That is the difference, the sum of square values with the actual value minus the average, the whole square, is equal to actual minus the predicted, the whole square, and predicted minus the average. Agreed, learners? But what is the use of all these? So now there is this another factor, another unit which helps in comparison of value, that is R square. That is known as coefficient of determination. That is known as coefficient of determination, which is also known as the R square statistics, proportion of variance explained. The value varies between 0 and 1 and independent of the scale y, right? So R square is equal to SSTO minus SSE upon SSTO, SSR upon SSTO. So what is the advantage in short? Let's not get into the mathematics. That the R square value will always lie between 0 to 1. So the values which are more close to 1 are better fit as compared to 0. Yeah, mean square error and RMSE relationship is clear, but they are not relative errors. I cannot do comparison between the different models, that this model is better than the other. They are good to tell the errors are less or more comparison between training, but R square is a relative error. Even absolute error is not a relative error. What do I mean by that? What do I mean by that? Let me explain you with an example. For example, you scored 70 marks and I have scored 30 marks. Who scored better? You would say 70 marks, ma'am. You scored better than me. But I scored 30 out of 30. You scored 70 out of 200. Getting my point? So there, how will I find the relative? If I start taking percentage of this, that 30 out of 30 is 100% and 70 out of 200 is somewhere around 40-50%. Then I can do comparisons. Got my point? That is why we are now heading towards ratio between the SSTO, the total sum of squares, with RSS and SSR, taking into all account all the variability of the data points. And that's why I now reach on this R squared term. Now better? Is it better? Sum of square error ranges between 0 to 1, which measures the amount of variability that is left unexplained after performing the regression. And SSTO minus SSE measures the amount of variability that is explained or removed after performing the regression, R square, and the proportion of variability in Y can be explained using X. So R square is trying to take into account all the errors and variability of the data point. So when R square is equal to 1, SSE is 0, that means it's a perfect fit. It's an ideal situation. Will it ever happen? Hardly. I don't think so. It's going to be, but something which is close to 1.99 is a good. And when I get this horizontal line that you all were getting, that means R square is equal to 0. Error is equal to total. That means there is no linear relationship between X and Y. Now clear? Right? But R square suffers from one limitation, right? Since R square is also known as if it is greater than 1, it can never be greater than 1. That's the Simon, that's not possible mathematics. Can percentage can ever come beyond 100%? The formula is such, now because we're taking a ratio out of 100, right, Simon? So mathematically, it can never be true. Got it? Okay. So R square, also known as the coefficient of determination, measures the proportion of the variation in your dependent variable X and explained by your independent variable X for the linear regression model. But the problem that R square also suffers is that it will always remain or increase as we are adding more number of independent variables. So this problem is solved by adjusted R square. What is adjusted R square? That it measures the proportion of the variation, explain only those independent variables that really help. So what do? We divide the error by degree of freedom. Do you understand the term degree of freedom, learners? Might be thinking so many concepts. Degree of freedom is the number of independent variables, right? Suppose if they are 10, suppose if they are 10 input features, then the degree of freedom is n minus 1, that is 9. Clear? How many input features are we depending on, Abhinetri? That is referring to my degree of freedom. It's something like, now let's understand it over here. Now, if I want to predict the price of the car, what are the factors that are determining the price of the car? Safety is a very, very important factor. How many airbags does it have? Does it have a parking sensor or not? The branding. What is the most important factor? The mile, the fuelage consumption, the fuel type in today's world, assistant, infotainment system. Is it a luxury car or not? The color, the kind of, the design, the seats, the wheel, the alloy. There could be several factors. Agreed, learners? But do you think the kind of wheels or the wheel alloys are as important as the engine of the car or the model of the car to determine the price? No, right? So that is what is taken care by adjusted R square, and when we divide it by the number of degree of freedom. Getting my point? See, normally what will happen is if I keep on adding the factors in R square, that I've added the number of alloys, the number of, the seat covers, the color of the car, the R square will keep on improving. It will give me an illusion, oh,
My model is giving so much well answers, but that's not true. Maybe, adding the kind of wheel alloy is not that concrete factor to determine the price of the car. See, these numbers of degree of freedom, as I told you, this is some example that they are taken. Degree of freedom depends on the number of input features. So that is why adjusted R square is a better, way of determining the results. So if I get back to the file over here and now look at how I calculate the results. So what am I trying to do? From Scikit-learn metrics, import mean square error, R square error, and then I do the prediction. Prediction is done by the predict function for the training output as well as for the testing output. And then the different metrics can be simply calculated in Python by using the mean square error for training data, for testing data, and R square. And then I can do the comparisons. So if you see the training error is 0.573 and testing error is more than that, that's more closer. So they all refer that the model is underfitting. Now clear? How are we trying to fit the model? How are we trying to uh, fit it, then predict the output, and then calculate the error? So if we talk about linear regression, let's look at it again. That this is my actual output, right? And if I talk about a single variable as my input, and there are two coefficients, beta naught and beta 1, this is the epsilon error. Is this first equation getting clear to everybody? Simple linear regression, single variable is getting clear to everybody. Then we have linear regression, multiple variables, right? We have x1, x2, x3, right? Epsilon over here refers to the random error. And if we talk about a model evaluation, are we clear with these metrics now? The mean absolute error, the mean square error, and the root mean square error, right? So comparisons between the different models is not possible. Therefore, we have R square error, which talks about the ratio, and even better than R square is adjusted R square because it is not affected by the number of inputs in the data. Clear? So basically, we divided by degree of freedom mean model. Clear? And we have also understood different scikit-learn objects. Please try to understand fit function. Fit function helps us to train the input parameters or train the parameters for the data. Transform is transforming the input to output. Fit underscore transform is mixing the function of fit as well as transform. And it is the predict function which is used to predict the output of the training data or of the testing data. To understand it better, types of sklearn objects are based on transformers. Transformers are nothing which transform the data set. Have you learned feature engineering, learners? Do you understand feature engineering? Where we do feature scaling, standardization and normalization, encoding of the data, that we need to transform the data before we actually fit into the model. Let me try explaining you over here. So before the data is actually fed into the model, it needs to be transformed. Why it needs to be transformed? Because if they are missing values that will not fit into the model, if they are categorical features, then we have to involve encoding. Feature scaling is a feature which brings the data into one particular range, and outlier detection. That is why data science is important, because these concepts are covered in detail. How do you deal with data? How do you handle missing values? How do you deal with categorical data? Scaling of the data is all part of the feature engineering process. So in feature engineering, we are not just building models, but we are playing matchmakers for data as well as algorithms. Getting my point, everybody? Okay. So getting back for transforming the data set, right? So fit learns. What does a fit function do? It is an estimator. Please try to understand. Fit is an estimator which estimates the model parameter based on the training data and hyperparameters. And finally, we have the predictors. That is, it predicts the data, makes the data set as input and does the prediction. Score method to measure the quality of the predictions. Getting my point? So here we have the data pre-processing, training, and inference model. Clear? And then we have fit and fit underscore transform, right? What do we do that when we are trying to train the data? What I'm trying to explain, let me explain it with a slide. That again, please try to understand. Let me rewind things. In supervised learning, we have label data. First of all, what is label data? That we have the input as well as the output. Now, in the story, have you understood two types of output in supervised learning? That we will have the actual output of the label data, and one we will predict the data using the X test. This point is getting clear? What this point, which I'm trying to explain regarding the output, is getting clear, right? So this is output actual as well as predicted. Now we also understand that we divide the training and the testing data, right? So ultimately we are trying to, when we are doing training, it is all on the training data by the fit parameter. So the model, all the training will be done using the fit function in simple terms, right? And the testing and output will be on the predicted. But if I want to transform the data, so I will fit it and then transform it. And can I do the function of fit and transform together? Yes, by using fit underscore transform function. Getting my point? Can I do the function together? Yes, for only training data, I can use fit underscore transform, and for testing data, I will only use the transform function. Now clear? Okay. Okay, so now let's, once we have understood, now let's get back to the code. So now, are we able to also understand how when the model is underfitting and overfitting, that point is also clear? Yes. And if we talk about non-linear regression, polynomial regression is a subset of linear regression that includes polynomial terms. The relationship between the independent variable x and dependent variable y is modeled as an nth degree. So here we are not trying to do it as a straight line, but polynomial regression, which is a subset of linear regression, which includes polynomial terms. The relationship between an independent variable x and dependent variable y is modeled as nth degree polynomial, right? So why polynomial regression is called a special case of multiple linear regression? Some polynomial terms are added to multiple linear regression equation to convert it into polynomial regression. So it is a linear model with some modifications made to increase its accuracy. The data set used in polynomial regression for training is non-linear. So what do we observe? That in this particular graph, this is a straight line, linear regression. And if I change it to a curve, it becomes polynomial linear equation. Do we see that exponential curve over here? Okay. So I have this, simple data, right? In this simple data, this is the project statement, okay? Wait, live. Okay. Yeah, so a certain spare part manufactured company once a month in lots which vary in sizes. Data on lot and size numbers and man hours. That means the input is the lot size of the people and how many man hours are required, right? It's numerical, right? So if I start analyzing the data, actually, it's done through an Excel. It's simple that I do X minus X bar, Y minus Y bar, and I calculate this. What is this known as? RSS, residual sum of square, actual minus the output the whole square, xi minus xi the whole square. Do you see this? And why am I taking the square value? Because I simply take the difference between y minus y cap. The error is 0, which is actually not. Therefore, we take the square values and I get the answer as 13,660. Okay. So the sample size, the number of rows in this data set is 10. Degree of freedom over here is 9. Mean is equal to x bar sigma xi upon n 50. Variance over here is this much. Standard deviation is in this much. So this is where statistics is coming into picture. We have calculated the value. Similarly, we can calculate it for the man hours yi. Okay. And if I try to see the relationship, it's coming out to be straight line, right? Now coming on to the concept of how do we calculate the best fit line, right? So this is the least square concept where we are trying to find out the RSS. So over here, what am I trying to do? Again, yi minus the y cap the whole square, not this one. Okay. Here it is doing hit and trial method, but ultimately the least square estimators can be found out by trial and error method, but that is not the case. We try to calculate it by the normal equation. This is the equation for calculating of beta naught and beta 1. So these are already predefined formulas which run at the back end when I run the linear regression function. So this example shows that whatever values you are getting by solving mathematically or through linear regression model, I get the same values. Okay. So what does polynomial regression on data set work? Again, we are using the TV marketing.csv features. From the Scikit-learn pre-processing, we are including the polynomial features. Again, first we are splitting the data. So now I am creating an object of polynomial features, right, with degree equal to 2. And now I am using the fit underscore transform function, not the fit function itself, but the transform function because I'm transforming the input values as well as fitting, but I'm only and only transforming the output. Do I want to train the testing data? No. Why don't I want to train the testing data? Because, so if I give you what is going to be, if in your test, if I tell you the questions, is it actually a test? No, that calls for paper leakage. If I tell you what questions are going to come for an exam, that is known as paper leakage. And the same concept is known as data leakage over here. Getting my point, learners? So are you understanding the difference between fit, transform, and transform? The fit underscore transform will only and only work for training data. Transformation will happen for input as well as output. Will happen for training as well as testing. But fit will only happen for training data. When I create an object of linear regression, I get this output. So basically, the polynomial features transformer is configured to generate polynomial features up to 4th degree. Then we are only transforming the input to generate a new feature set that includes polynomial, features, and interaction. Then we transform the test data, correct it from fit underscore transform. It is used on x underscore test to apply the same transformation, and then train the model. The linear regression model is trained using the transform training data. Clear? And finally, we are going to predict the output and then create a graph, right? Do you see the scatter plot is testing data and plot is X range polynomial predict the output. Now clear? You are getting all the code how the graph is getting created. So what is the observation? And this is exactly, why Jupyter notebooks are hit in the market, because we are able to see the graphs over here directly, which VS Code lacks, right? We can see the code as well as I can write my observations also. So as you can see, the regression line is able to fit majority of the data points. You can infer from the above implementation that non-linear inputs require non-linear model such as polynomial model. Clear? So, I mean, linear regression also has capability of dealing with non-linear data up to degree 4, but not very high non-linear data, right? Then we have different variations of the algorithm. And if we talk about performance metrics for analysis, why different metrics? Because it calculates the average of the squares of error, which is differences between the actual and the predicted. Then we have the root mean square error. Oh, I hope you all are clear. Mean absolute error, R square error. Zero value indicates model explains none of the variance in the dependent variable. The independent variables have no exploratory power for the changes in Y, and 1 represents a perfect fit. The model explains all of the variance in the dependent variable. The change in Y are perfectly captured by the changes in the X. Clear? So now we have to start understanding another technique, important technique. Okay. So now let's understand what is cross-validation. And before we understand cross-validation, we need to understand few more concepts. Now in machine learning, there are two terms that you need to understand. One is parameters and other one are hyperparameters. Okay. So now what is the difference between parameter? A lot of learners get confused because they both think they are the same thing. No. Again, I'm telling you, I try to give you exactly, the crisp concepts, differences between them. So when I talk about parameters, they are values learned by the model during the training. So during the training, what the model learns is referred to as parameters, and hyperparameters are defined by the user to control the learning process. Purpose over here is it directly impacts the model predictions. So model automatically learns the parameters, and that is directly impacted in the output. Whereas hyperparameters are controlled by us. For example, how much is going to be the training data and the test data is a hyperparameter, test underscore size of train underscore split. Right? The factors or parameters which are controlled by us during the training process or model fitting process, that are known as hyperparameters. Whereas when the model learns the parameters on its own using the fit function are parameters. Clear? They are estimated during model training. They are generally, estimated before the training begins. Learn from the data using optimization, whereas the hyperparameters are set They are usually set or tuned using the methods like grid search, random search, or Bayesian optimization. Influence on the model affects the output directly, affects the speed and the quality of the learning. And this is dependent on the data set. These are independent of the data set. So the model parameters are nothing but your coefficients beta naught, beta 1, beta 2, or they can also be represented by weights in general. So generally coefficients become weights. That's the general term used in deep learning. Whereas the test underscore size, the number of iterations, and there are several other factors that will be controlled by us, even random underscore state are all hyperparameters. Is the difference getting clear? Right? So now, what is the need of cross-validation? Do we cross-validate results? Do we like to cross-validate views, reviews of doctors, lawyers? What does that mean, Abhinetri? And why do we want to do that? What does it mean and why do we want to do that? So that we are more sure of the answer, right? If one of the doctors is saying that you need to be maybe your disease has this and maybe you need to get operated, and even the other doctor says, that means you're more correct that yes. Or if the other doctor says no, doesn't need to get operated, you can cure it through these medicines, right? So cross-validation, or also known as rotation estimation or out-of-sample testing, refers to the process of rotating or splitting the data into different subsets. So it helps in the process of rotating, splitting the data into different subsets. Okay. So one part we are very, very clear that when we take the data set, we divide it into training and test. And definitely we don't want to mix any of their training and testing data sets to avoid any kind of data leakage. That point is also clear, that we want to avoid any kind of data leakage. That point also makes it clear. Now, to make our results better, more confident, more accurate, rather than using only one part of the set, if I use only one part or one sample of the set, if I use multiple samples, I can get better results, right? So this is my mini training data set. So it's always the training data set which gets divided into further training and validation split, right? So what is the idea? That we initially the data is getting split into training set and test set. Train and tune your models using cross-validation. So we will try to find out, okay, we want to make certain changes. This is better, not better, only through the training set. The test set is not involved. Test set we do not touch this until the very end, because ultimately that is going to give us whether the model is robust or not. Is this point clear now? So how do we go about cross-validation? So model evaluation is this: when we fit the model and then we predict the test set. That point is clear, that we have one data set that is divided into training and test set, right? This is normally that we do. We fit it and then we predict the output and do the comparison. But if I want to do model selection between different comparisons, what I will do, now the training data set is going to get divided into train as well as validation data set. What is the use of this model selection? It helps us to explore the hyperparameters grid. Now they are different hyperparameters. How do I know that this is the best hyperparameter for me? I will try to do it through the validation set. Fit on the train, evaluate on the validation, pick the best hyperparameter. Clear? Why are we doing this? Because we want to validate our training and results better. It helps us in finding out the different hyperparameters, right? So as we move along, more algorithms, you will understand it more. It's not part of regression, but part of supervised learning also. So cross-validation, when data set is too small for apply hold out strategy, then cross-validation can be used for evaluation and model selection. So what do? Suppose this is my 100 rows in data set, okay? And now I divided into 20 groups. So I have 5 groups, 1, 2, 3, 4, 5. So one of the part is going to be used for validation, other is going to be used for training. Then the next group is going to be used for validation next. So I will iterate it for 5 iteration. Got it? Of course, it is increasing the complexity, but it is giving me a much more validated result. Agreed? So one of the techniques or variants of k-fold is leave. This is known as leave one out cross-validation. Right? So we have 1, 2, 3 and n over here. Right? So if we take one part of the sample and the rest n are taken for training, then the next row is taken, the rest for training. So how many times the loop will be executed? N times. Is it a good idea? No. Taking each sample for validation and others for training is not a good idea because it will increase the number of computation. But if I have k-fold, that is, I divided into number of groups, my number of iterations decrease and I get better results. So how do we go about the performance and the output metrics, right? So what will happen? So the cross-validation will automatically create an array. In the first iteration, I will get the first metric. When it takes the second k-fold, I get the second performance metric. When I take the third iteration, I get the third performance metrics. The fourth one, and last one, I get the fifth performance metrics. Clear? So to answer that point, everybody please understand the test data is not touched. It is the training data and the different folds which I use, and final evaluation is done on the test data, whether I am getting the correct output. So the concept is same. We are doing comparison between training and testing, and that will give me the results, whether it's overfitting, underfitting, etc. Clear? Yeah. But when we talk about categorical data, what does categorical data means? That the data is in category in terms of males and female. So the folds we have, which have been cross-validated, will be taken up for final testing. Final testing will be on the test data only. Once the parameters have been found out, okay, the number of folds, okay, the number of, k value for this thing is this. So now we will test on this value. Are we getting the minimum results or not? It will help us to calculate the different hyperparameters. Got it? Okay, so when we talk about categorical data, dividing it into male and female. So this is my round one. So stratified k-fold is being used for categorical class, which helps us to keep the ratio of the different categories same. Okay, this we will do it when we do classification. Okay, so what is the difference between k-fold and stratified k-fold? K-fold is random. Stratified k-fold helps us to maintain proportions, may vary across folds, maintains class distribution across folds, imbalanced data set, not ideal, preferred use cases, balance and imbalance. And how do I check the metric that my cross-validation is good or wrong? First, my parameters for cross-validations are the estimators, input, output, scoring, and CV equal to 5. Estimator is equal to the model object. X is an array of the feature values. Y is an array of the target value. CV, the number of folds. scoring the metric, and it returns score, an array of scores at each split. So, the beauty of this particular function is that it returns at score of each iteration. So you're able to see which one is better, but generally we take the average of that. Clear? So now let's get back to the file and do it practically. So this file is quite long. We will be using this file in the next session. Of course, we will not be able to complete all the concepts today. So we are on cross-validation. After cross-validation, then we have regularization. After regularization, then we have hyperparameter tuning, that is model optimization, and then the pipeline. So it's a long journey that definitely we are going to continue. Okay. In this file. Yeah. So cross-validation technique. Everybody is there with me? 3.7.2. So what have you understood? What is cross-validation technique? Tell me, learners. So cross-validation is a machine learning technique that evaluates the model performance on unseen data by dividing the data into multiple folds. In each iteration, one fold is used as a validation set and the remaining as training. That point is clear? Then the process is repeated. So we have to give the number of iterations also. Yes, is repeated so that each fold serves as a validation set once, and the results from all iterations are averaged to provide a robust estimate of the model performance. Some of the common cross-validation techniques. Is k-fold cross-validation. K refers to the number of equally sized folds. That if it is unequal, it will make it equal by adding randomly some of the, randomly the data set only for the last one, right? And there is no harm also in doing it. Will not affect it much. So the model is trained on K minus 1 folds and tested on the remaining fold. That point is clear? So if I have 5 folds, then one of the fold will become the validation test and 4 will be tested. This process is repeated k times. So is this k also a hyperparameter? Yes. We decide they are going to be 5-fold, 6-fold, 7-fold, 8-folds, not the system. They are not parameters to the algorithm. It is decided by us, so it's a hyperparameter. And with each fold exactly once as the test data set. The results are averaged to produce a single performance estimate. We generally average it them. What is the advantage of k-fold cross-validation? It provides more accurate estimate of the model performance. Yes, that this is the answer. K is the number of folds. Yes, Ajay. And computationally intensive for large data set. Yes, you have to reiterate the training process, but it gives definitely better results. Clear? Then we have stratified k-fold. Similar to k-fold, but ensures that each fold has the same proportion of different classes as the original data set. This is especially useful for imbalanced data set. More reliable performance estimates for imbalanced data set, and still computationally expensive. Third is the holdout method, simple and fast. One, we divide the data into training and test, and the training data is further divided into training and validation data set. So the model is trained on training set and evaluated on the test set. It is simple and fast. The evaluation may be noisy and variability in the training. So the normal one that we do, we divide it into training and test, is known as the holdout method. And leave one out cross-validation is again a special kind of cross-validation technique used in k-fold. A special case of k-fold cross-validation where k is equal number to the number of data points in the data set. Each observation is used once as a test set. The model is trained on remaining data points. Clear? So this maximizes the amount of training data used. Cons, extremely computationally expensive, especially for the large data set. Clear? 4 variants of cross-validation techniques. K-fold, stratified, hold out, and leave one out cross-validation. Okay. Now can we begin with the code? So I hope everybody is familiar with the Pandas and the Matplotlib library. We are also familiar with the Scikit-learn model selection. These are the different techniques and metrics. Linear regression over here, and this metrics to compare mean square error, absolute, R square, etc. Clear? So here we are talking about housing.csv. So, yeah, take it as housing. So what are the pre-processing steps? What are the steps involved in EDA? Tell me. How do you perform EDA? You'll do head, tail to view the data, check null values, do info, right? So let's look at info. So if you look at info, it has around 20,640 rows and 8 columns. Do you see this? All are integer values. Do you see this? Yeah. Now the question is, can you tell me what is the output over here? Why it is a regression problem? What are we trying to do in this data set? Can you analyze it through the number of columns? Based on the latitude, longitude, housing, age, total rooms, bedrooms, they all are inputs. I am trying to predict the house value. What will be the value or the price of the house? House price prediction. Now clear? All these are my inputs and one output. House values are numerical continuous value. Therefore, this is known as regression. Clear? Okay, now let's see. The observation that price lies between 1.1 million to 2.6 million. Houses are generally 18 to 37 years old. Housing data. Let's check the null values. Yeah, now let's check the null values. So total number of bedrooms, we have 207 values. How do we deal with null values? Either we will replace it by mean, median, or zero. Since null values make up only 1% of the total data, rows and column features with missing values will be removed. So what are we trying to do? We are going to drop now because 207 is hardly 1% of 20,000 rows. So we can drop those data and now my data set is clean, right? And this is the categorical data which we are not using. We don't have that. And now can you tell me what does this mean, X and Y? Now I have dropped the median house value, axis 1, because that's my output. And now this becomes my output. This becomes my input, right? So if I say print X and then print Y. Do you see? Yeah. So now do you see this? So X basically has longitude, latitude, house, median, total bedrooms, etc. And Y is only that. So let's remove Y. Clear? So I keep making changes in the code. Are you understanding? So these are my now the input. And my output is median house value. And then I use the train test underscore split. Clear? Okay. Now let's perform k-fold cross-validation. It implements k-fold, number of splits is 10, divides the data set into 10 folds automatically, random underscore state is 42, shuffle is also equal to. So I have created an object of this k-fold. Now I initialize the model. There with me? And then I evaluate the cross-validation score based on the model. Model was linear regression, training data, and the target variable. Scoring, I'm using negative mean absolute error as the performance metric. So this is where the Absolute error comes into the picture. CV cross-validation is KF. Number of jobs is equal to -1. What does this mean? It utilizes all the available processors for parallel computation. Do we understand the concept of threading or the number of core processors, learners? So this parameter takes care of that. Okay. This parameter takes care of that particular one. Clear? So from statistics, import mean, I'll take the mean of the K-fold cross-validation. K-fold scores are not defined. So let me run this. Let me, show you that since the number of folds is 10, so the output of K-fold crow is an array object. See, do you see? They all are mean, negative, absolute errors. Negative does not mean that the error is less. It's just the sign. Okay. So we will try to take the average of these, right? There will be 10 outputs since we have given 10 folds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Clear? It's an array. And then I will try to take the absolute average of this. Clear? So we have trained the model and evaluate on the test set. So are we now understanding how are we going about cross-validation score, learners? And now finally, after cross-validation, now we can use the test data. So this is how I have fitted the data, predicted it through the test, and my MSE, test MSE is here. Similarly, my R square is here, right? So my test MSE and R square scores are here, right? Look at the error, it's so huge, indicating that on average, the squared prediction errors are large. This can be interpreted in context of units of dependent variable, which are likely in order. Since the numbers are very high, that is why the errors is coming out to be large. This can be mitigated by scaling the features. Feature scaling is critical in machine learning to ensure that all features contribute equally. So this is how, and then we demonstrate leave one out also. LOCCV scores, and we get the absolute mean score. Clear? So the mean absolute error is high. To improve the model, more complex model can be considered, which will be discussed in further lessons. So the concept of cross-validation is clear. Let's do a quick knowledge check on that. Okay, a quick knowledge check. First question. Which of the following cross-validation versions may not be suitable for very large data set with hundreds of samples? We just now studied that. I think so we've all seen it practically. Practical has a major impact. We all have just now seen the impact, and it is leave one out cross-validation. Great. Which of the following is a disadvantage of K-fold cross-validation method? Training algorithm has to return from scratch. Do we understand this? Every time it has to restart and do it again. Next question. Suppose you have picked the parameter for model using 10-fold cross-validation. Which of the following is the best way to pick a final model to use and estimate its error? Train a new model on the full data set. Using the parameter you found, use the average cross-validation error as its error estimate. So you can use average cross-validation error as its error. Everybody got this? Why C is not correct? Because we will train the model on the full data set. Okay. So what is the idea? The best way to pick, why is the answer B correct? The best way to pick a final model is to train a new machine learning model on the full data set using the parameter learned to use the average cross-validation error as its error estimate. So please be clear with this particular point. That is why I have added this MCQ. We can compare different models using cross-validation. Cross-validation is mainly used for comparison of different models. For each model, you may get average generalization error on the k validation sets. Then you will be able to choose the model with the lowest average. Clear? And cross-validation is also used for model checking, not model building, because it allows to repeatedly train and test on a single set of data set. Let us suppose we have a linear regression model and a neural network. To select the best one among these, we can use k-fold cross-validation. So to compare between the models also, we can use cross-validation to select a better performing model. Clear? So when we are now looking at the regression outputs, right, or the regression analysis, some of the outputs are like this. So the output over here that we receive is in these terms of coefficients, that this is my beta naught, this is my beta 1, beta 2, and this is my beta 3. So this is my north, south, east, and constant term. And these are the values, right? So what is it showing? This is the constant value positive. East has positive relationship, but south has more positive relationship with the heat flux. Heat flux is the output, and north has a negative relationship with the output. Are you now understanding it better? How do we get the output and how are we relating it with the the equation of linear regression? So this is nothing but like beta naught plus beta 1 x1, the value of east, plus beta 2 x2 minus. So a lot of you had questioned that how do we understand negative? It will automatically get this. So this is multiple linear regression. Yes, learners. This is multiple linear regression. And there was a lot of confusion regarding, ma'am, what does multi-collinearity mean? Multi means referring to multiple independent variables, multiple inputs with multiple regression. Call means joint or together, referencing to the linear movement or correlation. As I told you, it tries to find out correlation in terms of -1 +1 occurring within the linear equation. And suffix means the idea. So if we look at over here, from statistics, we understand that p-value is a very, very important term, right? That if I have the value lesser than 0.5, then this is accepted. This is accepted. This has a strong evidence, statistically significant. But if this is not lesser than 0.05, that means east is 2.12 is not very statistically proven or confident that the value is this. Clear? And when I talk about VIF, how do I calculate multi-collinearity? It is the variance inflation factor, which is coming out to be 1.21. What does that mean? This is the correlation map, a heat map that you understand. So multi-collinearity is the phenomenon of high correlation between the predictor variables can create instability and bias in regression model. To identify and address multi-collinearity, we use the variance inflation factor. So the VIF is equal to 1 minus 1 upon R square. And if the value is equal to 1, that means all the input values are independent. And if it lies between 1 to 5, it suggests moderate correlation. So over here, we are getting the value between 1 to 5. So there is moderate correlation, or we can say independent also. And if it is greater than 5, then it indicates high correlation. That means then linear regression cannot be can be fitted on that input values. So where VIF should not be used, polynomial equation, dummy variable, or a nominal variable. And multi-collinearity reduces the statistical significance of the independent variables. VIF is used to detect these variables. A large variance inflation factor on an independent Variable indicates a highly collinear linear relationship to other variables that should be considered or adjusted for structure. Because multicollinearity is one of the assumptions that we, assume when we are trying to build the linear regression model. So that means if the VIF value is greater than 5, then linear regression should not be used. Clear? I hope these points are clear now. First concept that we will learn, data leakage in machine learning. So now we will understand the concepts of pipeline today. Pipeline is a technique for automating different processes. What is the different processes that we do? Whenever the data is loaded, we want to do transformations such as encoding, scaling, right? So we'll try creating a pipeline, and what is our main aim? That we want to avoid data leakage, of course. Why? Because if there is data leakage, the data gets lost. A lot of information is also getting lost. So now if we look at the data from the supervised learning perspective, it is divided into two parts. One is known as the training data and the other one is known as the test data. Agreed? Okay. So a scenario when the ML model already has information of a test data in the training data. Do you think that test data should be present in the training data? If I tell you, okay, in your exam, these questions are going to come, that's going to be very beneficial for you for scoring marks. But do you actually learn out of it? No, that's not a good way of learning, right? That, it can give you good results, but you're not going to be a robust model. That means if any other question is asked from that particular topic, you will absolutely fail, right? But this information would be available at the time of prediction called data leakage. So what is the disadvantage and how can we avoid it? That it causes high performance while training set, but performs poorly in the deployment or the production. Okay. So when there is an, or if I say when there is an overlap of training and test data, then it causes data leakage, right? And basically, data leakage happens due to two reasons. First, we understand train and test contamination or the target leakage. What do we mean by that? Target leakage occurs when the model is trained on the training data that contains target or the feature information. So we don't want that, and that should not be available at the time of prediction. So we have to be very, very careful when we are doing this. The other one is the train test contamination is an event where the test data leaks into the training data and the data pre-processing steps for transformation, for example, scaling, encoding, are applied before the splitting the data set. So contamination is when the test data leaks into training there and the pre-processing steps. So that the scaling, encoding should not be applied before the splitting of the data set to avoid data leakage. Got it? Basically, if there is mixing of training data in the test data set, or rather test data in the training data set, then this causes data leakage. And we have to avoid it in every case. That is, we should not apply any transformation, that is scaling or encoding, before the splitting of the data set. Now clear? Now, another very important concept of regularization. There are two types of regularization available under regression, that is ridge and lasso. Preventing overlearning, Yes, normalizing the data. Yes, we can say that. So regularizing thing in a normal way, right? We want to prevent it from overfitting, overlearning, right? So regularization is a technique in machine learning which prevents overfitting of the model. And how do I know that the model has overfitted? How do I know that the model has overfitted? Test error much higher than the training. The training error, and why is it that the model is trained so complex than requires high variance? It covers every possible train outcome, making it Yeah, so the complexity of the model increase. It tries to train on each and every data point and fails on the final test data due to noise, due to learning of noise in the training data. So to avoid it, so as I've been telling you that in machine learning, do we suffer more from underfitting or overfitting? Overfitting, right? So we need methods so that our model does not overfit, and we need certain control parameters to achieve that. So there are two, algorithms under this, that is ridge and lasso. So lasso is known as L1 regularization technique. Can anybody tell me what does this term mean? Anybody? It is summation of the actual value or the true output minus the predicted output, the whole square. What is this term known as? It's an error. I want the typical name of this error. It is the residual sum of square error. But rather than only taking this error, actual minus the predicted value, the whole square, I take into account the another hyperparameter lambda, which I will use to control or regulate the training process. So do we have a regulator? Do we have a regulator to control the speed of the fan? Similarly, lambda, we will use the regulator. And similarly, summation of beta. Can anybody tell me what is this beta over here? What does the term beta mean? It is the coefficients. It could be a single, it could be many multiple variables. So this is known as the regression coefficients, right? Not the intercept or slope. That is only in two-dimensional case, like beta naught plus beta 1 x1. I agree. Both of you are correct on those perspective. But in general, betas are known as regression coefficients or the weights parameter. So what is the advantage that we are getting through this L1 regularization? That in the error term, in the RSS term, now we have added the penalty lambda, which is controlled by us and which controls the value of these regression coefficients. Getting my point? And in ridge regression, that is known as L2 regularization. So this is now also, known as my error, or it is also known as the cost function. Try to understand in deep learning, the error with which we are calculating becomes my cost function. In this case, it is represented as L over here. It represents it as my loss function. There is slight difference, but actually in machine learning, they all mean the same thing. Okay. So here we have the RSS W. Now what is this W over here? Is it the same as beta? Is it the same as beta? Yes. It's the regression coefficient. Is the lambda same? Yes. The lambda in Python is known as alpha. And then we have sum of the square of the weights. And what is this? Actual value, predicted value. Now are you understanding whether it's W or beta? They mean the same. And this is the lambda parameter with the square of the coefficients. Okay. So what are the advantages and disadvantages? And now then we will practically jump onto the file and start learning from there. So L1 regularization performs feature selection. What do we mean by features? Independent variables or the inputs? Yes, the inputs. So now we are trying to control. So now what is the use of overfitting? We understand that overfitting generally leads to high variance, agreed learners, and complex models. Agreed? Do we understand this concept, everybody? So to reduce the complexity, now I will try to control my coefficients, regression coefficients, beta naught, B1, and beta n, or in general, I can also call them as weights. Now getting my point. Do not get confused with the terminologies. Somewhere it would be written as weight, somewhere as beta, somewhere as independent variable, somewhere as features. So you should be able to understand the concept of it. Clear? So the beauty of L1 regularization is that it performs feature selection by shrinking the less important features weights to 0. So if I have a multivariable data set from beta 1 to beta naught to beta 7, it will shrink few of the features. That means some of the features or the weights will become 0. That means they have no significance relationship with the output. For example, if we want to, just try to listen and absorb as much as you can. That suppose, we want to predict the price of the car. Okay. So there are several factors from fuel to design to color of the car to the alloy of the wheels to the security systems to the infotainment system to the sunroof. There can be several features, but maybe the alloy of the car or the wheel of the car might not be important, so it can be reduced to 0. That will help us to reduce the complexity, and that will try to reduce the overfitting of the model. So very, very important concept. L1 is used to reduce or shrink the less important features weights to 0. So it helps us in feature selection, right? And it can also be used for high dimensional data set with many number of columns such as 20, 30, 50, 100 with many irrelevant features. And the disadvantage is it is not effective for data set with many important features. Now you might say, ma'am, how can we remove a feature? My every feature is important for the output. Then we use L2 regularization, okay? Where the value of the coefficients of the weights will not become 0. It provides a smooth solution and improves the generalization performance of the model. So, ma'am, Ridge is going to doing the opposite. Instead of 0, it is reducing the weight. Ridge is trying, or it is trying to see, the first one is making it 0 and the L2 will try to reduce the value. L1 is lasso and the ridge one is making the value of the coefficient small, not huge or big, but small. So therefore, the biggest advantage is that it can handle data sets with many important features. Okay, so now moving ahead to great, Abhinetri. Now let's get back to the file. Everybody has the file. Everybody is ready in the Jupyter notebooks. Okay. So regularization in regression. In linear regression, regularization encompasses a set of techniques employed to address the issue of overfitting. So what is regularization? Regularization is the method, techniques to achieve the objective by introducing a penalty term. Please try to understand. Again, it's a very, very important question from the point of interview. Introducing penalty term lambda to model's objective function to prevent it from overfitting. This objective function, typically measured by mean square error, is minimized during the training process. So generally, the error of the mean square error, or the RSS to be precise, is minimized during the training process. What is the advantage of that penalty term, or the lambda? The penalty term discourages the model from attaining excessive complexity by penalizing the size of the model coefficients. So, model coefficients, regression coefficients, beta naught, beta 1, beta 2, or the W1, W2, Wn, thereby mitigating the overfitting process. Got it, learners? All right. So now if we talk about the regularization term, alpha, it can be known as alpha as well as lambda. Okay. They all mean the same thing. It's written as lambda or sometimes as alpha. So do not get confused. Okay. So there is a little terminology mishap happening. So everyone uses their own technique, but try to grasp the concept. Okay. So alpha is the hyperparameter that scales the penalty term. It controls the strength of regularization. Higher the alpha, it imposes stronger penalty on the coefficients. That means they tend to become zero, leading to greater regularization. This tends to produce a simpler model that may underfit the training data, but often generalizes better to unseen data. If we talk about lower alpha, it imposes a weaker penalty, leading to a model that is less restricted by regularization and more complex, potentially capturing more details in the data, but at the risk of overfitting. So what are we looking at? We are definitely looking at a value which is not very high and very low. So again, minimum mid value to find out. Got it? How do we find it? What are the best methods? That we will understand today. That is known as hyperparameter tuning. That's part of this today's session also. Okay. Now, what are the benefits of regularization? It enhances the generalizability of the model. By mitigating the overfitting factor, regularization fosters model that can perform well on unseen data, reduce model complexity, it promotes interpretability, and potentially reduces computational cost associated with training complex models. And the two common regularization techniques are L1 and L2. L1 is lasso. Lasso is a full form of least absolute shrinkage and selection operator, right? So absolute term is there as the penalty. So Simon, is there any standard to label it as high, alpha or low? Yeah, we'll understand. Of course, low is my zero values or negative values, and high values are in thousands and lakhs. Let's do it practically to understand that point better. Okay. So is the full form of lasso clear to everybody? So which is the penalty term? Of course, it is the alpha or the the lambda. But what are we trying to add? The absolute value of the regression coefficient. So the least absolute shrinkage and selection operator regression relies upon the linear regression model, but additionally performs a so-called L1 regularization, which is a process of introducing additional information in order to prevent overfitting. As a consequence, we can fit a model containing all possible predictors. What are predictors? I'm purposely reading. You might feel ma'am just reads the data, but I'm purposely reading it to make you understand line by line. So what is containing all possible predictors? Predicted value is an output. Predictors are input. So we can fit a model containing all possible predictors and use lasso to perform a variable selection by using a technique that regularizes the coefficient. So what is that lambda parameter doing? It is having control on the value of the lambda or the alpha has, where it's controlling or regulating the values of the coefficients. The coefficients, the regression coefficients. That's up to you how you want to represent it as betas or weights, right? So it performs variable selection or feature selection. It forces some of the coefficient estimates to be exactly equal to 0 with the help of large tuning parameter. So more the value of the lambda, some of the features coefficient value will turn out to be 0. And that is why this is a technique which is also used in dimensionality reduction. What is dimensionality reduction? Reducing the number of features in the data set so that it reduces the complexity. So L1 again plays a major role in that. It helps to reduce learning of more complex data and overfitting. It decreases the variance of the model without increase in the bias. All right. So in minimization, objective does not include RSS like the OLS regression, but also the absolute value term. So this RSS now is clear. This is the residual sum of square. And this is how we can expand it and write it. This point is also clear. What is yi? This is the actual output. And what is this output? This is the predicted output. Are you all understanding it mathematically, conceptually? But in lasso, where does the difference come? The RSS is the same, but we have added the penalty term alpha or lambda along with the absolute value of the summation of the coefficients. Now clear? If the alpha is equal to 0, then there is no regularization that will happen because the error term will be same as the RSS. If it is equal to infinity, all the coefficients will become 0. And if the alpha is greater than 0, lesser than infinity, coefficients are between 0, that of least square linear regression. Got it? Is the theory part clear? Now let's move on to the practical part. Start with a new data set. So let me share it with you, hitters.csv. Okay, here we go. Please download this data set and be ready. I hope different libraries are also clear. The NumPy Pandas, then linear model lasso, the matrix mean square error, R square. All these are there. Okay. So basically now let's understand the description of the data set. So I have provided a link over here. So this is for we have now IPL matches. So here we are trying to predict the salary of the player based on at-bat, number of times he batted in 1986, hits, the number of hits, the number of home runs, the number of runs, the number of runs batted, walks, number of times a bat during his career. So lots and lots of parameters to decide the salary of the player. That is 1987 annual salary on opening day in thousands of dollars. Got it? And then we have another important column that is new league, a factor with A and N indicating the players league at the beginning of 1997. So what is the first step? We've loaded the libraries, we load the data set and the view of the data set with df.head. Okay, what are the other functions that we would perform? Info. So this data set is quite huge in the sense that it has the number of rows are only 322, but the number of columns are many. So this is an object data type. At-bat, everything is integer, but we have league, division as categorical data. And then we have salary over here as the output and new league. So what are the different steps that need to be performed? Can we directly apply the model onto this data set? So these are my columns. So I have used df.drop unnamed equal to 0. Encoding, if any. Do you think encoding is required? Encoding is definitely required for league division. for all the columns which are of object data type. Please remember this point, learners. Encoding is definitely required for object data type. Without that, you will not load it into the model. Duplicate values, if they are, then we need to check that. Okay. We are removing unnamed column because that is not required. We are specifying the access. What does in place equal to true mean? Permanent removal of that column from the data set. So now if I see my first column gets removed, so the first processing that I have done. Now let me check the null value. Are there any null values over here? Only the null value is in the output, in the salary field, right? Which is my output field. Agreed, learners? Do I need to separate my X and Y also? Yes. So the number of missing value in salary is 59. So 59 out of 322 observation with null values correspond to columns salary. Since we will use the lasso algorithm from the Scikit, we need to encode our categorical also. Okay. Now, how do we deal with categorical data? What is the use of value underscore counts function? It gives the category along with the frequency, along with the count, right? That's incomplete. It gives the category along with the count. So in league, there is A and N with these categories. In division, there is W and E, Western and Eastern. And again in new league, we have A and N, the American League or the National League. So if I separate this into a data frame, do you see this data frame rather? This code is getting clear to everybody. Are we here? Till here? Okay. So what are the different ways of encoding data? One is one-hot encoding, other one one-hot encoding, other one label encoding. What is the difference between the two? One-hot encoding adds column and then gives the binary output. If that column value is there, then it has 1, else all values are 0. Yes. And label and assign integers to each of the category. Yes. And label encoding is used when we have a ordinal data. One-hot encoding is used when we have nominal data. That means there is no order. So over here, we are using which function, learners? Yes, it is now one-hot encoding that now it will have, instead of 3, 6 columns with 0 and 1 value. Right? So do you see this? League A, League N, Division E. Do you see now? So wherever we have value of league, get underscore dummies is one-hot encoding and label encoder, that is the function. So is the output of dummies.head is also clear? That now if these are the 6, the 3 categorical value can get converted into 6. And wherever the value was there, this is 1 or this is 0. This is 0 and this is 1. Clear? Okay. So what are we doing? We have separated the output. X numerical value, we are dropping the output, the league, the division, and the new league because they all are categorical data and everything gets converted into float type. So the numerical columns are now clear. The input X numerical and the output Y salary. Good, Chakrapani. Good. Now, do we need to concatenate these columns with the original data? So we'll just take one of them. Since it has binary category, please try to understand. Since all of them have binary category, therefore it can be used for league underscore N, division underscore W, and new league underscore N. Getting my point? So now you see all my inputs have become integer values, numerical values, and that is what is required before you feed any data into the model. Now, once my data is ready, now we go in for testing and splitting of my input and output. Test size is 25%, rest is training, and I get my 4 outputs, right? So lasso, performs best when all the numerical features are centered around 0 and have variance in the same order. Homoscedasticity needs to be maintained. And if a feature has a variance that is orders of magnitude larger than others, it might dominate the objective function and make the estimator unable to learn from others. So it should not be that, one of the columns have very high values and the other one low. This means it is important to standardize our features. We do this by subtracting the mean from our observations and then dividing by standardization. What is this concept known as? Or feature engineering. Okay, I've given you one hint. This is the concept involved in feature scaling, and this refers to standardization, that is, scaling the factors with mean equal to 0 and standard deviation equal to 1. Clear? To avoid data leakage, standardization of numerical features should always be performed after data splitting only for the training data. Please try to understand. To avoid data leakage, we will only and only use it after the splitting of the data. We saw that. So what is data leakage? We understood what is data leakage. That it occurs when the information from the outside the training data set is used to create the model. This can happen if the data would not be available at the time of prediction is included in the training process. So data leakage can lead to optimistic performance estimates and models that fail to generalize well to new as well as unseen data. Clear? So, which is the Python function? Which is the Python function to perform standardization, standard scaler, which creates an instance of the object fit. Fit trains the X-train numerical data, that is, training means to find out the parameter to compute the mean and the standard deviation for each feature in X-train list underscore numerical. X underscore train is your for each data set, and the list numerical is the list of column names corresponding to the numerical features. Got it? What is the use of transform? It applies to the standardization of the training data, which transforms each feature in the training data set to have mean 0 and standard deviation 1, right? And then we only use the transform function on the test data. Now clear? Okay. Standard scaler is clear. It's the function to perform standardization. Standardization is one of the feature scaling technique where we take mean equal to 0 and standard deviation equal to 1, Anush. That point is getting clear? Fit is always performed on the training data, that is numerical data. Till here also this point is getting clear. That this refers to the list of numerical data. And transform, we are doing it on the trained data. That is how we are going to avoid data leakage. Now clear? Got it? But when we talk about, testing data, are we going to apply fit function on it? No. We are only going to transform it. So it applies the same standardization parameters, mean and standard deviation computed from the training data to test data. And this ensures that the test data is scaled in the same data as training. Now clear? Okay, right? So practically, how do we go about it? So we have imported the standard scaler from the Scikit-learn library, and then we perform this function. So the explanation is given above. Right? So what are we trying to do? We are fitting the standard scaler to numerical features so that there is no biasness in the data set. Now, you'll see positive, negative value because the sum of all these values should be 0. The mean of all them should be 0. Clear to everybody? So the training data has 241 rows and 19 columns. Clear? Similarly, test 1 will only have 81 rows because of the 25% data and 19 columns. Clear? Now they were missing values in the output data. How do we go about it? How do we go about it? Let's see. Yeah. So what are we doing over here? Yes. What are we doing? We are taking the training model as well, training data as well as the testing data and filling it with the median value. Wherever there is null value, it will fill it up with median. Not mode over here. Dr. Henry, we see it practically that it's getting filled with median. What is the difference between mean and median? Besides that, which one is affected by the outliers? Where do we use median? When we do not want to get affected by the outliers. So now let's move ahead and understand the lasso model. So whenever we have to create, how do we begin with the hyperparameters? If I want to start any of the models, how do we begin with hyperparameters? We will randomly assign any value and then start training on it. And to find out the actual value, we do hyperparameter tuning. So we apply lasso regression on the training set with regularization parameter that is alpha equal to 1. So we begin with a very simple value alpha equal to 1. This value is commonly used as default and provides a good balance between maintaining model complexity and reducing overfitting. Okay. So by default, whenever we have to do things, you can randomly assign any value to the hyperparameter. Alpha is equal to 1, maximum iteration is equal to 10,000. And now we are fitting the training data. And this is now my new intercept coefficients, the regression coefficients, beta naught, and the other coefficients. Because since they are how many parameters? Can you tell me how many parameters are there in this particular question? How many are there? 19, all the numerical values, right? So we would have 19 coefficients. And do you see after applying lasso, some of them have become 0? This one, this one, this one, and this one. Getting my point? So if I see the output, these are my coefficients and some of my coefficients have become 0. Do you see? Then you might say, ma'am, what is negative 0? It just puts the sign. There is nothing, no term in mathematics as negative 0. Clear? So what do we conclude? This is the intercept term of your lasso regression model. It represents the expected mean value of the independent variable when all the independent variables are set to 0. In practical terms, it is the baseline prediction when no other information from the variables is provided. So the lasso coefficients represent the relationship between the variable. Positive coefficients. Now, what do we interpret out of it? Let's see that. A positive coefficient indicates that as independent variable increases, the dependent variable also increases. That's the positive relationship. A negative coefficient indicates that an independent variable increases, the dependent variable decreases. The magnitude of the coefficient shows the strength of the impact. Now clear? So the magnitude of the coefficient shows the strength of the impact. A larger absolute value indicates a stronger defect. Lasso regression is known for its ability to perform feature selection. So ultimately, the values have become 0. So now my 19 features have reduced to, so I have reduced these two. Then I have also reduced 2 above, and 1 in the last. So 3 features get reduced. So 19 gets reduced to 16, right? When we have taken lambda equal to 1. All right? Right? But in this model, however, it seems that none of the coefficients are exactly 0, suggesting that all included variables have some impact on the models, though some impacts are very, very small. So basically 4 features. Yeah, okay, 4 features. So now how do I evaluate it? I'll calculate my mean square error for the training data and then for the testing data. This code is also getting clear. That helps me to decide whether it's overfitting or underfitting. So now you tell me, is it an overfitting model or an underfitting model? Testing error is more than the training. So is it underfitting, overfitting? It's overfitting. And if I do the R square over here, so the value is very, very less. So to better understand the role of alpha, the regularization parameter. So what is alpha known as? The regularization parameter. Plot the lasso coefficients as a function of alpha. Maximum iterate are the maximum number of iterations. So here we have np.linspace function. What does the np numpy linspace function do? That now the values of alpha will range between 1 to 5 and with 10 equidistance value. So now what are we trying to create? Linspace function, do we understand of NumPy? So now if I say now I will start understanding the range of the values from 0.01, right, to 500, and the value is still 100, right? So over here, these are the values or the array created of alpha. The maximum iterations are 10,000. And now I will try to run or fit on each of these alphas. And then look at this beautiful graph. Simon, specially for you. So the value of the alpha goes from 0.01 to 100 and 1000. And we see as the value of the alpha is increasing, some of the coefficients actually become 0. You see this? So that is why L1 regularization is also known as feature selection. Agreed? Okay. So have you understood this graph now? So we create now the best value of alpha. How do we find out the value of alpha? That now we will use cross-validation to find out the best value for alpha. Lasso regression comes with built-in cross-validation. So beauty of Lasso is that you can combine Lasso with cross-validation. Alpha again ranges between 0 to 1000. CV is equal to 10. Maximum iteration 10,000. And n underscore jobs is equal to -1. Can you, anybody tell me what is the use of this parameter? Okay, I need to repeat that. Okay, Simon, I'll do that. In the meanwhile, tell me what is the use of n underscore jobs, learners? See, once we have checked on the training and the testing process, and we found out that it is an overfitting model, the test error was too high than the others. So now we have to find out the, the best value of alpha. Okay. Right, so to use the maximum course, and which is the, best alpha value which has come out. Over here, 6 comes out to be the best regularization. So get the best alpha regularization strength selected by the cross validation. Clear? So it was not, the value of alpha was not 1, but it will come out to be 6. And now I will create and fit the lasso model, taking this value. Now I will fit it and now check on my training and testing errors. So have they improved? Well, the test error is still higher than the training, right? But it shows a better performance on the tuned parameters. So zero coefficients such as runs, RBI, CAT, and all these new leagues have several coefficients shrunk to zero. This indicates the lasso has deemed these features less important, irrelevant for the data set, and the non-zero coefficients give us the detailed relationship. Clear? Moving on to ridge regression. Ridge regression is another technique for handling overfitting of the data. That's known as L2 regularization. Here, none of the features will become zero. Rather, values will become less, right? So, where it is used, when to use that and when to use the other one. Get the best alpha selection validation. Now, what is this? Added below library. Okay, so when is ridge to be used? It is useful for handling multi-collinear data where two predictors independent variables are highly correlated to each other. Right? And the second important reason, Ajay, you are absolutely correct. Ajay Kana, you are absolutely correct. But the second reason where we use ridge regression is that it is useful for handling multi-collinear data where two predictors, independent variables, are highly correlated to each other. Now getting my point? Collinearity refers to a situation where two or more predictor variables in multiple regression model are highly correlated, meaning they have a linear relationship, and this makes it difficult to determine the individual effect of each predictor on the target variable. Right? So that's why the penalty term is added, the regularization terms are added. Getting my point? So now let's see ridge. Again, we have a ridge CV function which can do. So on the same data, we will first apply the alpha fit function and get the intercept value. Yes, ridge needed to use if we want to keep all the important features. So I have not been running the code, so I will get error. So sorry for that. I'm not running the whole code, going back and running it. So now let's move and then evaluate the model. Again, testing error is more than the training. So overfitting is there. And do we see the coefficients now? None of them become zero. Now we can use cross validation again to find out the best value. These are the values. I have used rich cross validation, and in this case, the value comes out to be 204. Right? Then we train on it, and these are my new coefficients. These are my new coefficients, right? All values have reduced. If you compare with the original, all values have reduced now. So the negative error relationship is with errors, division W, they show the negative relationship. So the coefficients with highest value suggest cumulative career statistics, total runs, the total hits are most important and showing a positive relationship with salary. Division underscore W, the only feature which is notably high negative coefficient, which indicates that being in Western division is associated with negative effect on the target variable. So do not be in the Western division. Years assist and new league and these features are smaller. So are you understanding? This is how you're practically supposed to run the code and write down the observations over here. And if we see it graphically, that in this case, the values will not become zero, but near to zero. Clear? So have you understood the concept of regularization? How it helps in preventing overfitting, whereas L1 helps in feature selection and ridge helps in reducing the values if all are important. And of course, this analysis helps in understanding the relative importance and influence of different aspects of a baseball player statistics on the predicted target. Clear? Now moving on to the next concepts, that is optimization, right? Model optimization. Now, what does the term optimization mean? What is the meaning of model optimization? Optimizing resources. We want minimum number of code, less number of time to giving the best. Yes, how the model performs efficiently. Absolutely. So if we talk about the journey of data science or analysis, see everything if you are doing a normal Excel, maximum, minimum, drawing graph, that's also analysis. And even when we are doing machine learning, that's also analysis. But where is the difference? Are you able to get this graph that I'm showing? Where is the difference? Can you tell me? If we already have a data set, so this is the side for that. We are going to describe, about the historical data that we have. That is simple finding out hindsight in the data. When we try to find out why that happened, that becomes diagnostic analysis, that is insight. And if we move further, what is going to be predicted? Sorry. Or what will be the output? That becomes predictive analytics. And similarly, why that we are predicting that output, whether that is going to be good or bad, that is known as prescriptive analytics. So this is where we start from hindsight, insight, and now we want to move to the foresight. How does it happen? When we start optimization of the model. Are you understanding this point? Very, very important graph. From one analysis to another. To explain you in more layman language, suppose you have cold and cough, right? And you go to the doctor. Doctor sees, okay, your nose is running, you have cold and cough. He says, you take this normal medicine and, do a lot of steaming and take this medicine, you'll be fine. But that was his, analysis which he done to just by seeing you. So then you come back, you are not fine. Then you go back after a week to him. You say, no, I have fever also. I have other thing. Then he thinks that the fever, he is not getting well. So maybe he has some kind of an infection. Then he prescribes you certain blood tests. So based on the blood test, he would give you certain medicine. But you are still not fine. Your further analysis is needed. Maybe you have a chest infection now or something, and maybe you want to go in for an MRI. So that's how the level of analysis increases. All right. So basically, what do we want to do and what do we want to optimize in this whole machine learning process? That if we have this input data, that is the training data, including the target output. Of course, if it is supervised learning, we would also have the target output. This is my model, right? And output prediction calculated by model. So when we try to compare the predicted output with the actual output, therefore we are able to calculate the error and the loss function. Are you all there with me? Then we are able to calculate the error and the loss function. And using this error and or loss function, we can use optimization method to, further reduce the values. How we can further reduce its value. Getting my point? Right? So that's how we are trying to improve on the error part of it. And then another way to optimize the model is through hyperparameter tuning versus model training. What is hyperparameter tuning? That to find the best hyperparameters which give us the most efficient results. And This is a very, very important slide because it gives the whole crux of the data, of all the points that we have studied till now. Please look here. This is my data set. Feature engineering is performed before. What are the different aspects of feature engineering? And why is feature engineering required? Tell me. What are the different aspects of feature engineering and why is it required? To prepare the data to feed into the model, not tune, we will say to prepare the data, pre-process the data to feed into the model. And what are the different types? What is this step known as? Splitting, but what are we splitting and why are we splitting? It is splitting of the data set. Why are we splitting it into three parts? Normally it is training and testing. This step is known as cross-validation, that it divides the training data into training and validation and a separate test data. Second step is splitting of the data, yes, but we generally keep using it for cross-validation by taking multiple samples. Got it? By taking multiple samples. Now, this is an iterative process. This keeps on getting repeated. So the training data, we build models, train the results, right? And finally, once the training is done, then on the validation thing, we do the training results, do hyperparameter tuning, and keep on repeating this iterative process. Finally, the best model which is selected is then used for testing the output and compare the results. Do not get confused. See, every concept that we study has its own role and concept, right? So where will the regularization fit over here? If I compare the result, my testing result is much higher than the training result, then it is an overfitting model, right? We always start with the basic mega. Then we will use the model over here as ridge or lasso and then do the comparison. Now getting my point, everybody? All right. And the two types of hypertuning methods are grid search and random search. Grid search is the one in which it's an exhaustive search technique where we have different hyperparameters, one such as A, B, and C. It's not necessary that, we have understood that regularization has one hyperparameter. We have other models like decision tree, which have many hyperparameters, hyperparameter to XYZ value, and then we try to take all the combinations and then see which one works best for a model. Disadvantage of this method is it's an exhaustive method. Computationally and time-wise, it is expensive. Clear? And random search, that randomly we will select any hyperparameters and do training on it. Clear now? And we have seen, so cross-validation is a very, very important technique. Why? Because it helps to split the data into training, validation, and test set. Please make this point clear. Cross-validation technique will almost be used in supervised learning because it will divide the data set into three parts. That is training, validation, and testing set. Useful if you want to have a metric on how well your model is performing. Clear? So once the grid CV search returns with tune parameters, build the model using this set with the tune parameters and test the new model with the test set. Clear? And this is another, slide which I always show it to my learners even in my feature engineering class. Now, are you able to interpret this particular slide, everybody? Yes. right? So we again have a data set, retrieve the data set, perform pre-processing, wrangling, feature extraction, feature engineering, train the model, then model evaluation, hyperparameter tuning, and reiterate the process. But this slide gives a much better picture of each step. Got it, learners? So getting back to the file. So this file is pretty long, you know. Last week also we have done, and I think so this session also we would be using. So model optimization means hyperparameter tuning is the process of finding the best settings for the parameters in the machine learning model. Hyperparameters are settings that are not learned during the training, but are set before the training process begins. Hyperparameter tuning involves trying different combinations of the hyperparameters and evaluating the model's performance using validation techniques. So the two techniques that we can use is grid search. So how does it work? How do we do the grid search? It systematically works through the multiple combinations of hyperparameters. It performs an exhaustive search on a specified parameter grid. So how do we go about it? Please try to understand the different steps. The first step is we define a parameter grid that is defined with the help of dictionaries because they can be more than one hyperparameters in the model. Combination evaluation. The algorithm evaluates all possible combinations of these hyperparameters. Model training. For each combination, the model is trained, evaluated using cross-validation. And then we have the optimal parameters combining yielding the best performance. Highest accuracy is chosen as the optimal set. All right. And how does the random search work? It defines the parameter distribution, specify the distributions and ranges of the hyperparameter. Random sampling, random sample combinations of hyperparameters from these distributions. Model training for each sample combination and optimal parameters. All right, so now on the same hitters.cv, we are running the code. I might get a lot of error. It will. Let me run the x_train. Okay, so this is the grid search cross-validation. Here we are creating a cross-validation object with repeated k-fold function. Number of splits is equal to 10. Number of repeats is 3. Random state is equal to 1. Are you now there with me? Everybody, other code, else code is running. Then we create a grid or a dictionary and then try to find out the values. So still it's giving error. Is it running for everybody else? Oh, well, I've tried to do a shortcut, but shortcuts never work in life. Value y input consists of nan. Okay. Yeah, are you getting it? I'm not running the code. So this point is clear. So the best parameter grid of alpha, now it's coming out to be 0.9. Is it the same with everybody? So then we create and fit the ridge regression model to avoid training data with the optimal alpha. So here we have the ridge function results into best parameters alpha, fit them through the training input as well as output and find the mean square value that comes out to be 341. And R square comes out to be 0.38, which suggests a moderate fit. The model captures some of the variability in the data, but not a large portion. And now if I see the coefficient, this is how the coefficient values are. Now let's move on to the next concept, last concept by creating pipelines. So Scikit-learn pipelines are nothing but an automation of the model fitting and data transformation steps for training and data set. So what are we doing at the moment? When we upload the data, we separately use fit and transform, do encoding, do scalar standardization. Now we will try to implement it with the help of a single pipeline. So what do? If we have test data, test labels, we would perform feature scaling, standard scaler initially. Then if feature selection or extraction, dimensionality reduction is required, that can also be done. And then the model data can be fed to the different models. So how do we go about it? We are very clear in supervised learning. We have a training set and a test set with class label, right? So in the first step, we will try to fit the training data that is missing in the test set because we do want to avoid data leakage, right? The fit function will never ever work for the test data, right? And therefore, we have the fit transform function over here. This is the pipeline, right? So over here, we do the transformation such as for scaling, dimensionality reduction, and then do the predictive model. And over here, it is fit and transform for the training data, but for the test data, it is only the transform function. Clear? And the predict will only be for the test data. Now let's see how do we practically implement it. So why Sklearn pipelines? Pipelines provide an organized approach to managing your data, pre-processing, modeling the code. They combine the pre-processing and the modeling steps into a single streamlined process. Cleaner code pipelines eliminate the need to manually manage training and validation data at each pre-processing step, reducing the clutter and the complexity. Fewer bugs by bundling steps together. So bugs are few. It gives a much more cleaner code and easier to productionize. That is, they simplify the transition from a prototype to a model to a scalable, deployable solution. Clear? So we have Sklearn is a beautiful library. We just need to, create a class, or we do import the pipeline function, and we will create an object of pipeline class, whatever steps that we want to perform. Do we want to use any kind of memory or verbose? Clear? So a pipeline is a sequence of data transformers that can include a final predictor also, final output also. It lets you apply pre-processing steps to your data in order and optionally end with a predictor for modeling. Each intermediate step in the pipeline must have fit and transform methods, while final step only needs the fit function. Memory stands that you can use cache memory for these transformations to make the processing fast using the memory argument. The pipeline main goal is to combine multiple steps that can be cross-validated together and have their parameters adjusted. You can set parameters for any step by using it name followed by a underscore. So you can set any of the parameters by default followed by a underscore name and the parameter name. And you can replace any steps estimator with another estimator or remove transformer by setting it or pass through or none. So now over here, they are using a different data set. That is the one with ocean proximity, that is housing one. I think so I gave you for testing also. So it is little different from original because one of the parameter is categorical ocean underscore object. So how do I check that? What are the different categories of this particular function? How do I check that? So we have this categorical data. So what are the different encoding techniques? Either we use one hot encoding. That is better because there is no order in this. So we'll not use label encoding. We'll use get underscore dummies function to perform it. Value underscore counts function is a function in Python which gives the categories along with their frequency count. Very, very important function. What is happening in this particular code of line number 46? Come on, learners. Y is getting the output value, and then we are separating the X. Yes, we are defining input and out. What is happening in the next step? Line number 48, what is happening in the next step? Splitting of the data, very, very important. And then we see the info and sum over here, right? So where are the null values? Where are the null values? Total bedrooms has 162 null values. Data is huge, 14,448, right? So definitely cleaning is required. Removing of the null values, encoding is required, right? So rather than now performing each of these steps separately, can I use the concept of Scikit-learn pipelines? First, I will feed in for training data, perform feature scaling, feature extraction, and ML algorithms, and then work on the test data. Getting my point, learners? Okay. So what are the steps that we want to perform before building the model? Feature engineering steps. So feature engineering part is used as Scikit-learn. Even the other parts can be combined as pipeline. First, missing value treatment, imputation. 162 missing values in the total bedrooms, numeric data column. Then we have the dummy variable creation for categorical data. And finally, standardization of the numerical value. So how do we go about it? These are my different libraries that I will import, and most importantly is the pipeline library. Getting my point? A very important concept in Scikit-learn is the column transformer. That importing column transformer class to apply different pre-processing steps to different subsets of the feature. So column transformer has the capability that encoding is applied only on categorical data, not on numerical data. Getting my point? So it will only be applied on categorical. So let me explain this. Okay, so this is how the fit transformation happens. But if these are my features, which is a combination, obviously, of numerical, categorical, and others. So column transformer has the beauty that for numerical columns, only scaling will happen. For categorical, one hot encoding, and maybe others can simply pass through. It's not necessary that some operation needs to be performed on it. And finally, we can get a transform data in very one go, and it can be combined together. Got it? Column transformer concept is clear to everybody? So here we go about implementing it. So now when you read about column transformer, you will understand that it allows you to apply different pre-processing steps to different subsets of the features in your data set. This is particularly useful when you have a mix of numerical and categorical data that require different types of pre-processing. Column transformer ensures that each column or group of columns gets appropriate transformation before combining the results for further processing or modeling. Okay, so now step 1. Let's store the names of the numeric and object type variables differently. So how are we going to do? And now we have splitted the training and the testing data, and we are exclusively selecting the data types: include object, exclude object, and result. Are you understanding this code, learners? So housing underscore cat will only have one, since this data set has only one categorical data, that is ocean underscore proximity, and the rest are all numerical in nature. Clear? Now, the next step says to set up Scikit-learn pipelines for numeric variables, we need to perform missing value imputation and then standardization. So how do we go about it? Now we will create a pipeline object using this pipeline function, num underscore pipeline. So for numerical data, we will import, do the missing value imputation and standard scaling. Is this point getting clear? Simon, are you there? Are you understanding this code now of creating pipelines? Yes, learners. What is imputation and what are we trying to achieve over here? Imputation is the concept of missing value, and here we are filling the missing value with the median value. Good, good, Megha. Very clearly it says that, right? And standardization is that we are trying to create the mean of the data 0 and standard deviation equal to 1. Then unified data processing with pipelines and column transformer. Now, we need to create another pipeline. No. So we've created a numeric pipeline. Now we create a column transformer, the numeric pipeline, and the other one categorical. For categorical data, we only need to perform only and only one function that is known as the one-hot encoder function. Clear? So this ensures both numerical and categorical data are pre-processed approximately within single unified work. Now got it? The beauty of column transformer that we have combined the numerical as well as categorical values. Okay, then we do pre-processing fit underscore transform x underscore train. We're going to fit and transform and now check the data set for training. Clear? Now do you see? It has already done this. So, right. So now we fit and transform and now check the training data. This is my training data. And now if I check the scaling has already happened, negative values are there, as well as the null values have been removed. Got it? Pipelines, are you understanding? So what is our observation? Good to see all missing values are treated, numeric values are standardized, ocean proximity is converted. Now, the other way of creating model is again, you can create a final pipeline for pre-processing and model ridge. Over here, we are creating ridge regression model straight away and then moving ahead. So have you printed that also, the final pipeline also? Yeah, so final pipeline gives you this, that after applying the basic thing, we are applying the ridge model, right? And then we define the grid of hyperparameters to search. You can set parameters for any step. So over here, this is my ridge alpha, the hyperparameter, which will range from 0.1 to 2.1. And then I use my grid search CV along with cross validation. Estimator is my final pipeline. These are my grids that I have passed onto it. Scoring, I'm using negative mean absolute error. Number of jobs is equal to -1 and we fit and get the output. Clear? So the mean absolute error is 49,000 and the alpha value is coming out to be 0.1. Then I check my test result. The test result is slightly higher, so it's almost a good fit of the value. Now clear? How, and even in classification model, we would be using a lot of pipelines to get the result. Getting my point? So finally, today, after Scikit-learn, we come to the end of regression analysis, which is, part of supervised learning, predicting numerical value. Regression analysis is an essential method for estimating, examining, and predicting variable relationships. In this lesson, we as we had discussed initially, types of regression, then the different error matrices, the cross-validation technique, the regularization technique, hyperparameter tuning, and then finally the pipelines. Are we all now clear with this particular file 3.2? Finally, we are ending with regression today. First question, what is the primary goal of regularization in machine learning model? Why do we want to do regularization? Yes, if we want to prevent overfitting. Which of the following is a characteristic of L2 regularization? Squaring of the value. Which answer is correct? A, B, C, D. Quick learners. It is both B and C because it adds the squared magnitude. It's rich of coefficient and it reduces overfitting by reducing the model complexity. Next question. What effect does increasing the alpha parameter in lasso regression have on the model? Lasso, do we want to increase model complexity or decrease? Obviously, when alpha increases, the model complexity. What is the primary difference between L1 and L2 regularization in terms of the effect on the model coefficients? Remember, L2 means squaring of the value, L1 is absolute. So it's simple. L1 encourages sparsity. What is sparsity? Having value 0. So it makes most of the features equal to 0. Well, while L2 regularization does not encourages sparsity. Now clear? How does regularization help in improving the generalization ability of a machine learning model? We want to reduce the variance or the bias? Overfitting. Overfitting gets reduced by variance. What is the risk with tuning hyperparameters using test data set? What will happen if we tune hyperparameters? What is the risk with tuning hyperparameters using test data set? The model will overfit the test set and data leakage can happen. Which of the following is not the purpose of optimizers? They try to avoid overfitting because that's the work of regularization. If searching among large number of hyperparameter, you should try values in a grid rather than random value so that you can carry out the search more systematically and not rely on chance. True or false? We should carry out more systematic searches or random searches when searching a large number of hyperparameters. Right? False. You should try values in a grid rather than random values. Why? Because then it would become an exhaustive search, right? We should always try random values. I hope this knowledge check was helpful for everybody.
Start with another part of supervised learning, that is classification. Now tell me, how will you define classification? It is supervised learning used when the output is categorical, right? Yeah. So this is supervised learning technique when the output is categorical. So these are the independent input variable and the model classifies them as animals and fruits. So are you aware about different classification techniques, learners? Do you understand different classification techniques? Do we understand the concept of binary classification? What can you interpret from this particular diagram? That the model will classify the input or not input, sorry, the outputs into two categories. For example, if a mail is there, it will either put it into the spam folder or the inbox. So when there are two categories as output, that is known as binary classification. Getting my point, learners? Can we have more than two classes as output? Can we have more than two classes as output? Yes, we can have, when we want to label different vegetables such as capsicum, carrots, tomato, radish, turnip, it could be endless number of classes, and that is known as multi-class classification. Are you all getting this point, learners? That is known as multi-class classification, learners. What is this? Suppose I have an image and in the image there can be multiple labels. This image consists of a truck, boat, dog, as well as a plane. So if we have more than one, it's not multi-class, but a same, you know, image or a same input. For example, a movie can be romantic, thriller, horror also, right? Or comedy, thriller, horror. So the same item can have multiple labels. That is known as multi-label classification. What do you observe over here? If the classes are not balanced, right? The images of trucks are around 60% plain, only 25% boats, 15. Then there is a different techniques to deal with imbalanced class data set. All right, so this basic concept of different classes is clear. Now let's straight away dive into how we will analyze the classification output, right? Or what are the different metrics to analyze the classification output? So what do you think? How will I check whether my model is classifying the mails and the spam mails correctly? The metrics which is used or the major role that is being played is done by the confusion matrix. Please try to understand. For example, I'm taking a very simple example. There is a bag of balls of red and green balls. Now, if I tell you to classify them, it is good that in the red ball bag, you put all the red balls, and in the green ball bag, you put all the green balls, right? So that is true positive and true negative. So the green balls which belong to the green bag are in the green bag, and the red balls which belong to the red bag are in the red bag. But is there a possibility that a red ball can be in a green bag or a green ball can be in a red bag? Is that possibility? Yes, machine can create those errors. And that kind of errors are known as false negative and false positive, right? When the machine does not predict the correct output. So what is our aim as a model? We always want to increase the true negative and true positive to create the best results, right? And we always want to decrease the errors, that is the false negative as well as the false positive. Getting my point, right? So a confusion matrix, please remember again, it is very, very important point when we always talk about classification, that a confusion matrix is a n by n matrix used for evaluating the performance. And that is why statistics is said to be the strong foundation for machine learning concepts. Bang on, Mega. Appreciate this. Yeah. So confusion matrix is an n by n matrix used for evaluating the performance of a classification model where n is the number of target classes. So it will always be a square matrix. A good model, as we have understood, will have high true positive and true negative rates, and whereas a low or a bad model will have high low true positive and true negative rates. So what do we do when we have imbalanced data set? That means the ratio of the classes is not same or equal. It's always better to use confusion matrix as your evaluation criteria for your machine learning model. So this is how you will get the output in terms of your Python code. It will create this kind of a matrix and display for you. And I hope the terms true positive and true negative, false negative are clear. True positive is predicted positive, which are actually positive. False positive, predicted positive, but are actually negative. Getting my point? And this is the exactly the same example I always use in my hypothesis testing class also. I use the same example. All right. So this is a very, very interesting example. We have the images of cat and dog, right? So we have about 20 images of cat and dog, right? So for cat, they were only 7 images, and dog, they are around 13 images, right? So I, ran this particular images on the model. So 6 images, which were actually cat, were predicted positive by the model. So that becomes my true positive. 11 images which were not cat were actually predicted that they are not cat. They come under the true negative category. So very good. But the errors were that the image was of the cat, but it says that you are a dog. So one error over here of false negative. And similarly, the image was of the dog, but it says that you are a cat. So this is false positive. So the false negative errors are known as type 2 errors also, and the false positive are known as type 1 error, or also known as alpha and beta. If you remember from hypothesis testing, same concepts, absolutely same concepts are being used. Are you understanding this? So they are different metrics that can be evaluated from this confusion matrix: accuracy, precision, recall, F1 score, FPR, and FNR all can be calculated. So if I talk about accuracy, accuracy simply measures how often the classifier makes the correct prediction. It's the ratio between the number of correct predictions and the total number of predictions. So what does accuracy mean? I'll take my true positive, true negative divided by the total number of output. That gives me accuracy. But what is the illusion over here? The illusion over here is that it is not valid for imbalanced data set. Anu says, why type 1 and type 2? Why type 1 and type 2? Is there a possibility that the classes might not be classified correctly? So type 2 and type 1 actually arise because I am considering one of the statement as positive. Positive means that the image is of the cat, and negative statement means that you are not a cat, right? So false positive error means that actually it is not a image of a cat, but still says you are a cat. That is why false positive, that it is not a cat, and false negative because it is not a dog. The same game we play between null, but we'll be resolving it into different metrics. So one of them is accuracy, the other one is precision. So the precision is defined as the ratio of the total number of correctly classified positive classes divided by the total number of one predicted. So precision is useful when, please try to understand, precision is a useful metric in cases where the false positive is a higher concern than false negative. What do we mean by that? That false positive is a higher concern in precision. So what is more deterring? Whether, the mail is not a spam, but the model predicted as spam. Is that more important than a mail which was spam and model predicted as not spam? Getting my point? So if our important mail is considered as spam, then that is a serious issue. Therefore, the precision needs to be high. So what is precision? It is true positive upon the true positive plus false positive. Getting my point? All right. So the other metric that we can use is recall. Recall is classified as the ratio of the total number of correctly classified positive classes divided by the total number of positive classes. Or out of all the positive classes, how much we predicted correctly. So recall should be high and ideally 1. And again, where is the recall function mostly used? It is useful metric in cases where false negative trumps false positive. Getting my point? So what would be the case where false negative is important than false positive? For example, medical cases where it does not matter if we raise a false alarm, but actual positive cases should not go undetected. Got my point? So this is the formula for recall, the true positive divided by the true positive plus false negative. Clear? Ma'am, do we need to calculate all these formulas? No, you just need to understand the mathematical intuition. The Python programming will do it all for you, right? So some might say, ma'am, sometimes, the false negative error as well as the false positive error, both are important, right? Then how do we go about? Then the metric which is used to balance it out is known as the F1 score. So the F1 score is a number between 0 and 1, and it is the harmonic mean of precision and recall. So the definition already has the formula. Okay, harmonic mean. We use harmonic mean because it is not sensitive to the extreme values. So F1 score is valid when we have imbalanced data set because it maintains a balance between the precision and recall for your classifier. If your precision is low, the F1 is low and the recall is low again, and F1 score is low. So what do I mean by that? This is the harmonic mean and this is the formula. So F1 score is the harmonic mean and it should be ideally equal to 1. So there will be cases where there is no clear distinction whether to use precision or recall, then we can use the F1 score. Got it? So again, a quick recap. Accuracy is used when true positive and true negatives are more important. Accuracy is better metric for balanced data. False positive is much more important. Use precision. Whenever false negative is much more important, then use recall. F1 score is used when the false negative and false positives are important. Now clear? This gives you more clarity when to use what and where. And how do we create this confusion matrix in Python? By simply importing Scikit-learn matrix, import confusion matrix, and running the confusion underscore matrix function. So this is my Y test, Y predicted, and this is how I get the output in form of two-dimensional array, right? But the best part about it, that simply by using Scikit-learn metrics import classification report, we can get all the metrics in one particular output. This is what we actually use. Is it good 85% accuracy? See, if you're not, see, Simon, it's a very, very relative question, right, Simon? Obviously, 100% is perfect. But depending on the model, the kind of problem that you are facing, if you're not getting accuracy more than that, then this is the best. But if you can get accuracy up to 92, 95, or 97%, then of course, 85% is not acceptable. You are the one who's going to decide whether to accept or to reject the project. Or you want to make further improvements or optimizations onto it. All right. So this is a very, very beautiful, code that, for classification, that we will have this classification report in which we get all the output, precision, recall, F1 score in one tabular form. All right. And this is what we are going to actually use for, comparing the results. Getting my point? So again, a quick recap: accuracy, precision, recall, F1 score, specificity, and different metrics can be calculated. But as I told you, we do not use different metrics. We will straight away import classification underscore report and get the output. Now, another very, very important factor, how graphically we can judge the output. So in classification problem, we have AUC and ROC curve. What does AUC stand for? AUC stands for area under the curve and ROC stands for receiver operating characteristics. This material is not there in the Simplilearn file. This is my material. I'll be sharing it. Even the regression material, classification material, right? So another very important factor to understand classification is the graph AUC and ROC curve. AUC stands for area under the curve and ROC stands for receiver operating characteristics. So AUC ROC curve is a performance measurement for the classification problems at various threshold settings. Now, what do we mean by various threshold settings? That we will try to change the, that whether the classes have been classified correctly. The threshold value always ranges between 0 to 1. So it's like a meter rating. Okay, now this is a point or this is the boundary. Yes, these two classes have been classified correctly or the other two, right? ROC is the probability curve. Please try to understand ROC is nothing but a probability curve and AUC represents the degree or the measure of separability between the classes. So here we are trying to measure how well the two classes have been classified correctly based on the threshold value. It tells how much the model is capable of distinguishing between the classes. Higher the area under the curve, the better the model is at predicting 0 classes as 0 and 1 classes as 1. Now getting my point? What do we mean by AUC? It represents the degree or the measure of separability. The higher the area under the curve, the better the model is at distinguishing between patients with diseases or no diseases. So how does it work basically? So this graph is drawn between the false positive rate on the x-axis and true positive rate on the right-hand axis, right? And this graph is, and this is area under the curve, and this is the ROC, the receiving operative. Sorry. So this is receiver operating characteristics. And these are the different formulas that we have just now seen. So sensitivity and specificity are inversely proportional to each other, whereas TPR and FPR are proportional. Okay. So sensitivity and specificity. Okay. Recall the name. Recall. Have we understood recall? Recall is nothing but the ratio between true positive and the true positive and false negative. Okay. The recall is also known as the true positive rate and the other name is sensitivity. Now clear? Specificity is opposite of this. This is true negativity divided by true negative plus false positive. So ROC curve is the plot between the true positive rate and the false positive rate. That point is clear. Across the all possible thresholds. So what is this threshold? The threshold value is always between 0 to 1 and in between, it tells how well the two classes have been classified, right? And AOC is very clear that it is the area under the curve. So the more the area under the curve, which is equal to 1, the better is the classification. Now clear, Anush? So ROC AOC curve is the area under the curve. It sums up how well a model can produce a relative scores to discriminate between the positive and the negative instances across all classification threshold, and the values will always lie between 0 to 1. So AUC is desirable for the following, that why do we want to understand the area? Why do we want to use this area under the curve? Let me go through it, and still you have errors. I'll explain them. First, let's get the crux of it. I understand a lot of points are there. First, let's get the crux of it. Area under the curve is scale invariant. It measures how well predictions are ranked rather than the absolute value, right? So it's scale invariant. It tells how well the predictions were ranked. It's not absolute value. It helps in comparison. Secondly, it is classification threshold invariant, measures the quality of the model's predictions, irrespective of what classification threshold is chosen. So this is what I mean by my threshold. Generally, it should be like 50-50%, generally 50-50%, that my true negatives have been classified as true negative, green balls in green bag, red balls in red bag, and the total area under the curve is 1. So this is one of the ideal situations. This is one of the ideal situation that there is no overlap. Area under the curve is 1 and the model has ideal measure of separability. Now moving on to the next point. If we see it practically, even if my threshold is 0.5, there would be some, errors that, the red ball going into the green bag and the green ball going into the red bag. But these should be less. And if my area under the curve is close to 1, around 0.9, 0.8, or 0.7, then also it is said to be a good classification problem. So AUC 0.7 means that there are 70% chances that the model will be able to discriminate between negative and positive classes. Now getting my point, everybody? Now are you understanding the meaning of threshold? Now if I decrease the threshold, suppose if I make it to 0.2, what will happen? My false negative error will become less, but my false positive error will become more. So the threshold, we have to try to always create a balance to get the minimum errors. Okay. Now look at over here. This is the case where the model was not able to differentiate between negative and positive classes. One of the worst cases, that area under the curve is 0.5. So we don't want the area under the curve to be equal to 0.5. So this is a worst situation where area under the curve is approximately 0.5. The model has no discrimination capacity to distinguish between the positive classes and the negative class. Now better. And what could be the even worse situation? That the true negatives have been classified as true positive and true negatives, positives as negative, and the area under the curve is 0. So when AUC is approximately equal to 0, the model is actually reciprocating the classes. It means the model is predicting a negative class as positive class. And do we want this situation? Never. We don't want this situation. Area under the curve to be 0, area under the curve to be close to 0.5, but close to 1 is a good option. That means the classes are able to distinguish each other clearly. What is the role of threshold? Classification threshold in machine learning is a boundary. At what boundary, as I told you, we will cut the two classes or cutoff point used to assign a specific predicted class for each object. Any machine learning algorithm for classification gives output in probability format. That point is also clear. So in the morning also I was teaching the LLM. So LLM chat GPT is, predicts the next word. They all come under the category of classification problems and they all give the output in terms of probability. Okay, so a little bit of Gen AI and LLM models. So LLM, Chat GPT, your Copilot, all the different models, they are all come under the category of classification problem and generate the word based on probability. Okay, so that's the tip of the day today. So in order to assign a class to an instance for binary classification, we compare the probability value to the threshold, and if the value is greater than that, then the probability it belongs to class 1. If it is less than that, it belongs to 0. So the story of threshold is like this, that what is the cutoff point that we can achieve to get the best distinguished classes? That if you increase the threshold, you move left on the curve, and if you decrease, you move right to the curve. Okay, so let's get back to the file. So now we are on lesson number 4. You can go ahead with 4.1. So there are a lot of algorithms that we would be covering in this classification: logistic regression, naive-bayes classifier, KNN, decision tree, support vector machines. So today we will be touching on to the classification algorithms. Let's see how many are we able to do. Let's logistic, naive Bayes, and KNN. Definitely we are doing 3. Let's see if we are able to begin with decision tree also. Let's see. So now if I ask what is the definition of classification, how will you define it? Tell me, what is the definition of classification? Yes, learners. I am purposely asking you these questions so that you have the, clarity of the concepts, and then you are also well prepared for the interviews. Supervised machine learning algorithm using categorical data. Always say it is part of which learning technique, and where the model is trained to predict the class label. The output is important. When I say label the output of the given input data, so it is important that the output is categorical. Getting my point? Please try to cover all the points in the definition. If you're going to just put 3-4 words, it will never give you a complete answer. Getting my point? Okay. So classification is a supervised machine learning technique used to predict the category of class of n observations based on the training data. So I think so this definition is quite correct. So classification algorithms categorize data into different categories. So do you think that in classification there is a role of this, straight line or linear regression? Do you think that can we use a straight line to separate two classes? Let's see. Since linear regression is a simple function, let's see, can it be used? But before that, classification, examples of classification in healthcare, whether you are diabetic or not, or your medical condition is there, all come under the healthcare category. Finance, banks, financial institutions are classification algorithm, whether you are eligible for loan or not. Marketing, classification aids in customer segmentation and target marketing. It helps business identify potential customers and tailor marketing strategies by categorizing customers based on their behavior. Retail, in retail, classification algorithms are crucial for managing inventory, forecasting demand, and manufacturing. Classification is essential for quality control, fault detection. So there is no domain where classification problems cannot be used. I hope you all are getting this point. In retail, marketing, manufacturing, HR, everywhere. Right, learners? Now, what are the different types of classification that we have understood? Can you tell me? This is what we are going to try to solve, Roshan. Can we use regression in classification problem? This is we are just about to solve it. We're just about to solve it. Just be patient. Okay? Okay. So what are the different types of classification? What is binary classification? So when the model is able to classify only two classes, for example, whether the mail is fraud or not fraud, or spam or not spam, comes under binary classification. Already predefined, yeah, to classify into predefined multiple classes, whether it is a tomato or whether it is a vegetable, it is a fruit, or it is an animal, or is it a domestic animal or pet. So many classes can be used. One to many? No, Chakrapani, that's not the correct way to answer. The model is capable of predicting more than one classes of the input. That's the way to answer it. Multi-label, multi-label classification. Be careful while answering this, that each data point can be assigned multiple labels simultaneously rather than just one. Yes, simultaneously, like in an image, it can have an image of a dog, cat, rat, a chair, etc. Okay. And the last part is imbalance classification. What is imbalance classification? When the classes are there, they can be two classes or more than two classes, but they are not equally balanced, right? One class, like 70% of males are there and 30% of females. When the classes are do not have the same frequency count, or we can say when one class has higher significantly more than other observations, right? When one becomes a majority class, other one becomes a minority class. Okay. So binary classification, under binary classification, some popular algorithms are used. So please try to understand. Binary classification can be achieved by logistic regression, naive Bayes, KNN, decision trees, and support vector machine. We are supposed to, do all of these. So while these methods excel in binary, capable of handling multi-class. So, except logistic regression or other are capable of handling multi-classification task also. This versatility allows them to be used in wider range of applications such as recognizing multiple categories of objects in images or predicting several types of behavior. So now we'll start with logistic regression. Before that, let me also let's do a recap. Now, what are the different metrics involved in classification? How do I judge that my classification problem is correct or not correct? Confusion matrix. Yes, so what are the different components of a confusion matrix? Accuracy, precision, recall. These are the different metrics, but components of confusion matrix I said components. True positive, true negative, false positive, false negative. Absolutely correct. And based on these components, we calculate different metrics which can be used to analyze the classification model. So if this is my data and I divide the data, because classification also comes under supervised learning technique. So if this is my data and I divide it into training and test set, and the training set over here we have, right, from the training we develop the model. Test set is used for model evaluation, and we understand for classification problem the different metrics used are accuracy, precision, and recall, right? So it's a quick revision again. So this is my end-to-end matrix. If I have two classes, what are true positive and true negative? So when the output is also true, the predicted value is also true. When the output is false, when the predicted value is also false. But what are the two types of errors? What are the two types of error that we analyze in confusion matrix? Type 1 error is also known as alpha, or the false positive error, right? The type 1 is also known as the false positive or the alpha error. And type 2 error is also known as the beta errors. Clear? Then which metric is to be used when? We have accuracy. When out of the prediction model has been made, what the percentage is. If it is an imbalanced class, is accuracy a good metric to be used? Right? If we have more of positives, right, true positive, right, out of all the yes, how many them were correct, then we use the precision. Recall and sensitivity are the same. When we want to answer the question how good the model was predicting at real yes events. Recall and specificity. So there is this always this confusion about recall. So recall is associated with specificity also and sensitivity also. The question can accuracy. So F1 score. So F1 score is a more matured score which can be used, which is not biased towards the precision or recall. And it is used when dealing with imbalanced data set, meaning that they are more of one class label than they are of the other. It corresponds to the harmonic mean of precision and recall, right? And what is the graph that we understood, which helps us to identify whether the two classes have been classified correctly or not? If you remember that graph, learners, the AUC, it's AUC and ROC curve. ROC stands for receiver operating characteristics. AUC stands for area under the curve, right? So what was that graph telling me? This graph generates probability value instead of binary 0 and 1. It should be used when your data is set roughly balanced. The ROC is imbalanced data set leads to incorrect interpretation. So ROC curves provide good overview of trade-off between the true positive and the false positive rate for binary classifier using different probability threshold. So the value, if the value is below 0.5, it's a poor classifier. 0.5 random classifier, but if it is 0.7 or greater than 1, we can set that it is a good classifier. Now clear? So this is how we understand the ROC and the AOC curve is between the false positive rate and the true positive rate, right? And if we look at the more closer look at the AUC and the ROC curve, this is my X, this is my Y axis. This is my optimal threshold. Practically, we are going to draw this graph also and the selected threshold. The ROC curves gives a quick visual understanding of the classifier's accuracy. The closer to the right angle curve, the more accurate the model is. So more closer it is to the right. Classification threshold that turns the upper left corner of the curve, minimizing the difference between the true positive rate, false positive rate is the optimal threshold. Clear? Okay, so now let's go ahead and understand the first algorithm for classification, logistic regression, that is transform linear regression, which gives output between 0 and 1. So there was this query of you all, can straight line be used for classification problem, right? That was the query. So when I say, binary classification, how do you think that binary classification would appear? Yeah. So I'm asking you, how do you think that binary classification points would actually look in the graph? Tell me. Yeah. Maybe not a straight line always. Absolutely correct. Right? There can be on the either side of the straight line, right? So if I say it's a typical good binary classification data, it's a typical binary classification data that either the output will be 0 or the output, this is an ideal situation. Agreed? Either the Y will be 0 or the Y will be 1. Do you all agree? So now tell me, is a straight line a good fit on these data points? Or is it covering, is it consistent, or is it underfitting? No, this is not a good fit. And moreover, the values are also getting lesser than 0, some of the values, and some of the values are greater than 1 that we don't want. Because in binary classification, the output will either be 0 or be 1 in ideal case. Agreed? So now I need to modify this straight line into a sigmoidal curve or an S-shaped curve. Is it helpful for me? First of all, the values will always be within the range between 0 to 1. Is this point getting clear to everybody? And suppose if I want to find out that my threshold value over here is 0.5. So if my value is zero point 0.2, it is very clear that it belongs to this class. And if the value is 0.7, it belongs to this class. Only the confusion would arise at 0.5. So it is up to me. The 0.5, I want to keep it on this class or that class. Clear? Yes, linear regression, that question that regression are incapable of solving binary classification problem. Why? Because the straight line gives underfit to all data points. The values can exceed greater than 1 or 0, right? So are all these points getting clear to everybody? Right? So how do we go about mathematically? So we understand this sigmoidal function equation is written like this, right? P is the probability 1 upon 1 plus e to the power minus y, where y is nothing but the, y can you tell me? It's like the linear polynomial, not even polynomial, multiple linear regression equation. Agreed, learners? So this is your linear regression. This is your sigmoidal function. So now if I start taking log on both the sides, so now on the left-hand side, this is the equation that log to the power p. P is nothing but the probability. We want the answer in terms of probability that the values will lie between 0 to 1, that is p upon 1 minus p, beta naught, beta 1 x1, beta 2 x2. So again, ma'am, are we need to solving the coefficients over here? Yes. Logistic regression is a modification of linear regression, but here also we are trying to find out these regression coefficients. Got my point? Is this point getting clear to everybody? So taking this point further, log px upon minus px is known as the log it function. Now getting my point? Where does the term logistic term comes from? Because of this equation, and simple px 1 minus px is known as odds of p. That's the technical term. So now you are clear that the straight line or linear regression is not capable of solving the logistic regression problem. So the straight line gets converted into the sigmoidal S curve because the predicted y lies within the range 0 and 1. I hope this is clear to everybody. So, ma'am, in probability, P is the success, 1 minus P is the failure of the probability, right? Same we are using. Absolutely, the concept remains the same. Yes. Okay. So, if I say what is supervised learning, what is logistic regression, please try to understand and try to answer all the points. This is what the interviewer will catch. How many concepts you have grasped. Okay. So logistic regression is a supervised machine learning technique primarily used for binary classification. In this method, we apply the sigmoidal function to the linear combination of independent variables and predictors. Now clear? Always say that it is a part of supervised learning classification problem. used for binary classification. And here we are applying the sigmoidal function to predict using the linear combination of independent variables, predictors of features. What does this mean? What does that mean? Independent variable predictors of features. This refers to the input part of it, right? Absolutely correct. Great. So this produces probability value between 0 and 1, and this probability represents the likelihood of a data point belonging to a specific class, positive or negative outcome. Clear? Now, the mathematical concept of logistic regression, it uses the sigmoidal function. The core is the sigmoidal function, sigma ZS. So over here, logistic regression is also known as sigmoidal function. This is how it will always range between 0 to 1, 1 plus e to the power minus z, where z is nothing but the linear combination of input. Multiple variable linear regression, and the output is in terms of probability ranging between 0 to 1. Are these points 1, 2, 3 getting clear to everybody? So now you're getting the crux of machine learning. You have to first understand the mathematical intuition of that algorithm or model. Then how do we implement it in Python? Understand it from three perspectives. As I always tell in my data science class also, first try to understand the concept, the mathematical intuition behind it. Second, how do we implement it in Python? And third, how are we going to interpret the output? All these things need to be taken into account. Got it? What is the cost function? What is cost function? The error function. How are we calculating the error function in logistic regression? That is calculated with the help of binary cross entropy. Please try to understand. The cost function used in logistic regression is binary cross entropy, which measures the differences between the predicted probability and the actual class label, where M is the number of the training samples, Y is the true label, Y cap is the predicted probability. Clear? What is the term optimization now mean, learners? Do we need to optimize our models also? See the concept, same concepts will be applied. So what is optimization? Why do we need to optimize the model? Tell me. Nobody understands. Why do we need to optimize? What is optimization? Extracting the best, right? Getting the best. So the goal is to find weights W and bias B that minimize the cost function. That is, this is typically done using gradient descent. So we'll try doing the gradient descent algorithm as we move ahead with further algorithm. Mostly in ensemble learning I've covered. Yeah, so basically we want the best output from the model. So now we are going to use the breast cancer data set. Do I need to share this with you all? Okay. Please download this and be ready. So this breast cancer Wisconsin diagnostic data set is widely used data set in the field of machine learning, particularly in classification problems related to medical diagnosis. This data sets consist of breast cancer cases derived from a group of patients who underwent surgery and had their breast mass tissue sampled, whether they are cancerous or not. And basically, there are two types of cancer. One is malignant and the other one is benign. Malignant, I don't know how I really pronounce it correct or not. And the other one is benign, right? And this data set contains 569 instances, each representing an individual sample of the breast tissue. Number of attributes, they are 30 numeric attributes computed from the digitized images of the tissue sample. These measurements of the cell nuclei present in the images. So based on that, we are there. So what are the different attributes or inputs in this data set? Radius, mean of the distance from the center to point. So it's not an image, just they have taken different parameters, which will help us to decide whether it's cancerous or not. Textured standard deviation of the grayscale, perimeter, area, smoothness, compactness, concavity, concave point, symmetry, fractal dimension. The target variable diagnosis indicates the cancer type, which can be malignant or benign. So what is the output? Diagnosis. And what are the two outputs of the diagnosis? Whether the cancer is malignant or benign. Now clear? Is the objective, please always try to give time on the data set. Without that, you will not be able to understand the analysis, what you're trying to do and what you are trying to achieve. So we will use this data set to explore and compare various binary classification algorithm, examining how their performance varies depending on the type, implementation of each algorithm, accompanied by the mathematical explanations. Yes, learners, are we good to go? Why do we do regularization? First, let's understand that. If regularization is required, then only we will do, Anush. Why do we do regularization? Tell me. Yes, if observed overfitting, if the model will overfit, then we will. Okay, Anush? Yes. Now clear? So now let's start implementing. So what are the steps in Python? Come on, tell me quickly, learners. What are the steps in Python that we need to perform? Tell me quickly. Importing of the libraries. I hope the basic libraries are clear to everybody. Then these are for the pre-processing model scaler. Pipelines. Have we understood the concept of pipelines? Can we implement it in classification? Yes. What is the concept of pipelines? EDA? What does EDA mean over here? No. We don't, yeah, we start with EDA, but first is import of libraries. I'm starting from very basic, Simon. So what is the use of pipelines? Tell me, learners. Yesterday we did Scikit-learn pipelines. Deployment after package. What do you mean by that? Organized workflow. Yeah, it's an automating workflow for building ML models. Good, Ajay. That's a better way. It's automating because we would do all the pre-processing in one workflow. That's the correct way of answering it. Okay. An Scikit-learn linear model, logistic regression and accuracy. My Scikit-learn version is 1.5.1. What about you, learners? Have you been able to load the breast cancer data set, everybody? With ID, diagnosis, radius mean, texture mean. Oh, so Subra, yours is higher than mine, right? So what do we observe in the info of this data set? Tell me. What do we observe in the info of this data set? Tell me. Where is my output? This is my output. And of course, it has to be categorical as malignant or benign. And all others are numerical values. You see, all others are numerical value. So do we need to convert the output categorical value into numerical? Do we need to encode the output? No. Ajay, we don't need to encode the output. Is encoding required? Yes, we definitely need to. because computer will not understand benign or malignant. All the categorical value need to get converted into numerical value. Okay. So df dot describe. Okay. So this is the ID. This is the radius mean, texture mean, the perimeter mean. Do you see this? The count, the average value, standard deviation, minimum and maximum. So you have to, observe whether the values are lying within the range or are they too deviated, right? Right. So this is if I do df.describe.t, then I get the values for all other parameters. So unnamed, do we see there are, complete null values? So can we drop off this column? So df dot drop nr, right? Access equal to 1, it is for the column. In place equal to true, we understand that means it will make the changes original in the data set. So now we will remove this column because it is of no relevance. Got it? So now my data set is ready or not? So when I do a df dot shape, it has got this particular data set has got 569 rows and 32 columns. Agreed? So this particular data set has 569 rows and 32 columns. And what is the best way to check categorical data? By using unique function, which gives me the different categories. N unique gives me the number of categories, but I always prefer value underscore counts function. That means it gives me the frequency along with the category. So they are 357 benign, cancerous patients and malignant 212 malignant patients. Got it, learners? And if I draw a bar graph or count plot of it, I get this type. Everybody is getting this point, learners? Are you all there with me, learners? Even in your project or in real world, always try to create graphs, write down the observation what the graph is doing. Right? Then again, which ID has been dropped? Which column has been dropped? The ID column has been dropped, and this is my original data frame. Got it now? Trying to plot a correlation heat map to understand the relationship between the features. The heat map visualizes the correlation between differences in the data set. So what does the heat map do, or what is correlation? Yesterday, we discussed about this. We've discussed this point. What are the values of correlation? What does the correlation do? What is the range of values of correlation? Tell me what is correlation, Pearson's relationship, which will always range between -1 to +1. Did I share that with you or not? So what are the values of correlation? -1 to +1. Positive correlation, yes. Negative correlation and no correlation. Yes, good, good. So you all remember, other learners? Great. So heat map is the map which gives me relationship between the various dimensions. So what do we observe? That there is high correlation value between radius mean, perimeter mean, and area mean. Whereas when we talk about other observations, feature groups, features related to worst, largest value of these features for being each image, mean and error, standard error calculations are grouped over here. Now tell me what is happening in the next stage. What is happening over here? That from Scikit-learn pre-processing import label encoder. Right. Label encoder is one type categorical encoding. Please try to understand the correct word. This is categorically encoding, and we are using label encoder, right? And only one column is categorical, that is diagnosis. And here I am trying to fit and transform only the diagnosis column. So now my benign and malignant values change into 0 and 1. Clear? Is this point getting clear? So now when I see my df dotted, I see now no M and B. Earlier, please look at the output, the column of diagnosis. It is in terms of M and B. Now I can see it in terms of 0. Can we define what is 1 and what is 0? How else? Yeah. So when 1 is malignant and 0 is benign. Yes, we can. Now what is happening over here? Yeah, so basically we are trying to separate the input and output and then split the training and the testing data, right? And after the splitting only, then we move to Scikit-learn pipeline, dot pipeline to streamline the pre-processing and the training process. Why do we do this? Why do we do this after splitting the training and the testing data? That the features in the training and the test sets are standardized to have a mean of 0 and standard deviation of 1. A logistic regression model is trained using standardized training data to avoid data leakage. We don't want our testing data to be part of the training data, otherwise there would no point be of the prediction. Got it? Right? So do we understand this pipeline function? What are the two things that we are doing in this pipeline function, learners? We are creating a pipeline. First step we are doing. What does standard underscore scalar do? Come on, learners. Tell me, it's not that difficult. We've all done the EDA part of it. What does standard scalar do? Feature scaling. Yes, standardization. And then we are applying model selection, logistic regression, which will be iterated 10,000 times and randomly the data 42 is getting selected. So till here, are we clear? We have splitted the data, right, into training and testing. Now, after training and testing split, and even the categorical encoding has been done, I am doing standard scalar function. What is standard scalar function? That all my data points will be standardized with mean equal to standard deviation equal to 1. Right? They will all be having that value, mean equal to 0 and standard deviation equal to 1. And next step, we will apply logistic regression on the data. Now better, Simon? Now clear? And finally, we go in for the pipeline dot fit. What does pipeline dot fit do? It will try to find out the parameters or the training data happens on input as well as output training data. Till here, so now when I do fit, it will automatically first do standardization of all the input points and then fit the model. And then we will predict the output using training and testing data. Clear? But since it is a binary classification problem, we will do not use simple predict function. We use predict underscore probability A. What does that mean? Probable outputs are needed that will range between 0 to 1. So this is my output, obtain the predicted output after training the model. Got it, learners? So now, how do I actually test? This is my actual label, this is my predicted label, and this is the probability associated with it. Are you understanding the three aspects of it? So when I do the probable A, it gives me the values in binary. Yeah, the values will be 0 and 1. The values will be 0 and 1. But will it be 0 or 1 will depend on the probability value. Got it, Ajay? This is what I was saying when I say about the LLM models, right? The probability decides what is going to be the output. And then we can calculate the accuracy score and the training score. So in this case, both of them are coming out to be quite same. So we can say it's overall coming out to be a good fit. But which are the metrics which are actually used for classification problem? Which are the metrics which are actually used for classification problem? The confusion matrix. Because it's a little imbalanced, not highly imbalanced, because if two classes were absolutely equal, then it would have been balanced data, 50-50. But it is somewhere around 60-40, I would say. Okay, Puneet? Value underscore counts on this graph is telling me it's imbalanced. Right? So the training and the testing accuracy is there. But ultimately, who is the judge? The confusion matrix. The components of confusion matrix are true positive, true negative, false positive, false negative. I hope these points are very much clear to you. So the provided confusion matrix provides a summary of the effectiveness of COVID-19 tests that identify individuals with the virus and those without it. So we have understood this concepts that the case correctly classified as positive and predicted also as positive. These terms are very clear. We've discussed it in detail yesterday and I had done a recap. So now significance of confusion matrix is in terms of these metrics such as accuracy, precision, recall, which is sensitivity, true positive rate, specificity, and the F1 score. Right, learners? And do we understand the formula? That's also we've gone in detail. So lots and lots of revision for you. Then we also understand the ROC curve or the AUC curve, which is used as a graphical representation of a classification model's performance across different classification thresholds. It plots the true positive rate against the false positive rate at various threshold settings. So true positive rate or recall at these settings. Clear? So what is our main aim in, plotting the AUC or the ROC curve? That the default threshold for many classification algorithm is 0.5, meaning that if the predicted probability is greater than 0.5, the instance is classified as positive. However, this threshold might not always be optimal, especially in the cases of skewed classes. Do we understand the term skewed? What do we mean by skewed class distribution, learners? If the data is not normally balanced, it is known to be skewed data. Okay. So the methods of finding optimal threshold, there are two ways. One is maximizing your Jordan's J statistics. In this, we will find out the value of J by subtracting the true positive rate with the false positive rate. The optimal threshold is where the statistics is maximized. This method balances the TPR and the FPR, aiming to maximize the true positive while minimizing the false positive. Closest point to 0, 1. Another method is to point on ROC curve that is closest to the top left corner, representing ideal classifier. Clear? An area under the curve also we are clear. Now getting back to the Python code. So again, confusion matrix, classification report, ROC underscore curve, all these are part of which library? They are part of which library, learners? Learn metrics. Be very clear. Sklearn dot metrics. Even the RSS, MSc, they were all under these curves. Clear? So the confusion matrix is created simply by calling the confusion matrix by passing the actual value, predicted value output, and based on that, I get this display. What do I observe? 70 are my true positive, 41 are my true negative. And if I talk about type 1 and type 2 error, it's quite less. So logistic regression is done well. It gives me 2 and 1 errors. Clear? And then the best way to go about is creating a logistic regression report. So over here, the precision is 97, 98 for 0 and 1. Recall, F1 score is 98 and 96. And if I look at the overall accuracy is also coming out to be 97%. So overall, this particular logistic regression has come out to be a good classifier for this particular data set. Clear? So over here, they've given in detail class 0, negative class. Precision is 0.97, 97% of instances predicted as class 0 are actually 0. 99% of actual class 0 instances are correctly predicted as class 0. And here we move ahead. Right? All of the detail is given over here. Okay. And finally, how do I do the judgment? That I need to do plotting of the ROC AUC curve, which shows the trade-off between the positive rate and the false positive rate at various threshold settings. The AUC value indicates the model's ability to discriminate between the positive and the negative classes. So parameters used in plotting are these many parameters. That first of all, ROC underscore curve is the function which gives me the different values of FPR, TPR, and threshold, right? And based on that, I'm going to calculate my Jordan's J and find out my optimal threshold value. So what do I observe? That optimal threshold value is coming out to be 0.4848 and ROC or the area under the curve as 1. So is it a good classifier? Area under the curve is nearing, it's almost 1. It is 1, not even almost 1. So it is a very good classifier. Getting my point, learners? So the ROC curve in the image reaches the top left corner, TPR equal to 1, FPR equal to 0, which indicates a perfect classification performance. The model perfectly distinguishes between positive and negative classes at various threshold settings. And the ROC curve for logistic regression model has AUC1. This model has perfect discriminatory power, and AUC of 1 means model correctly classifies all positive and negative instances without error. And the optimal threshold of 0.4867 defines the decision boundary for the classifier. Probabilities above this value indicate stronger belief that an instance belongs to the positive class, whereas the probability below this value indicate stronger belief that it belongs to the negative class. Clear? You know, this practical example has made all the points clear. So over here, are we doing any kind of sigmoidal function, anything? That's already part of the implementation. So again, I'm repeating this point. First, try to understand the mathematical intuition behind the algorithm or the model. Secondly, how we will implement in Python. And thirdly, how do we interpret the results? Is it a good model or not? Clear? Ajay says, ma'am, one doubt. Despite I seen that this model is perfect in matrix itself, what is the main purpose of seeing ROC curve also? See, ROC curve tells me whether the two classes have been classified. Are they well separated from each other or not? That is the idea. Is this more overlapping or not? So just to reconfirm things. It's not by just doing one test. If you are suffering from some problem, the doctor wants to reconfirm from different tests, maybe the blood test, MRI report, and X-rays or other things, something like. So it's something which is more visually appealing, tells us, has more impact. Yes, this is a good model. The confusion matrix also tells us, the different classification report also tells us, and AUC ROC curves also tells us. So there shouldn't be any doubt left, when we are doing our analysis. All the analysis should give the same result, right? So now do we understand this graph? Let's see. So now this is also one of the reasons the threshold is used. That if I take it as 0.5, any value coming above it, as I told you, would belong to this class, So distinctly, there is no overlapping. It distinctly classifies all the points, and any value which is lesser than 0.5 belongs to this class, right? So can we go in for a quick knowledge check about logistic regression and classification? So question number 1, which of the following metrics are used to evaluate classification models? Confusion matrix, ROC, and F1 score is calculated using confusion. What is a classifier? So when we talk about classifier, the output has to be categorical. So which one gives the output as category? It's both A and B? No. Output as a single discrete value or output as a single discrete value. So both A and B. Input can be anything, continuous or discrete. Yes, the answer is C. Next, false negative. What does false negative represent? Which option is correct? It's A, predictive negatives that are actually positives. Yes. In binary logistic regression, definitely it is C. The dependent variable consists of categories. Next question. Why is linear regression model output a poor predictor of probability? Why? Because D is the correct answer. It can give, it cannot, the range can be beyond 0 and 1. Next, the output in logistic regression problem is yes, equivalent to 1 or true. What is its possible value? So of course it is B. It would depend on the threshold value. Okay. So now we have naive Bayes classifier. Okay, now moving on to the next algorithm. The next algorithm is completely based on probability. So what is probability, learners? Chances of occurring of an event. And what is the formula? Mathematical formula of probability. The number of successful outcomes upon the total number of outcomes, right? What is the probability of getting a head when I throw a coin? It's 1 upon 2.5. When I throw a coin, what is the probability of getting head? What is the probability of getting 1 when I throw a dice? That is 1 by 6. But there is another concept which is associated, which is known as the conditional probability. Do we understand? What is the probability of event A given probability of event B? Do we understand conditional probability? This particular algorithm is based on that. Bayesian theorem. That's why data science is important. So learners who have done data science should be clear about the Bayesian theorem. Conditional probability or the posterior probability is equal to the likelihood function, that's opposite. What is the probability of event B given A into the prior probability A divided by the marginal probability? Do you remember this point or not? No? Posterior probability is directly proportional to the likelihood function. You understand this or not? Into prior probability. Okay. So the naive Bayes classifier, this is the formula. that if I have these random figures or, shapes, the classifier is capable of classifying them into different shapes or groups, right? And the basic formula lies in that the posterior probability is directly proportional to the likelihood function into the class prior probability divided by the predictor prior probability, right? So how is this, posterior probability actually calculated? It is nothing but the product of the likelihood function. Do you see this? X1, my first